Hi everyone, let me know if you can hear me. Okay, I think I'm audible, right? Cool. Let's get started. So today we are going to solve data structures PYQ, and like I will be taking only good PYQs, which means like if this is any trivial PYQ, then I will not be taking mostly. Okay, so let's just get started. Let me know if you have any question before I start. So thank you, Arnab. Ratul is saying that please take hashing PYQs. Yeah, we will be taking. Okay, cool. Let's just get started. So this is going to be data structures marathon where I will be taking good PYQs only, right? As I said. So before that, I just want to tell you one thing that there is one playlist on YouTube that is for BFS and DFS. If you want to solve all of the PYQs of BFS and DFS, then you should definitely watching that playlist. In this playlist, I have compiled many of the good questions from the PYQ and some of the standard university questions also. So this playlist is not that much long. I mean, if you take it, it is just a one session of marathon, right? So you can definitely watch this playlist. In this playlist, I have solved many of the good PYQs. Almost all of the good PYQs I have all the good PYQs I have covered, and some of the trivial PYQs also I have covered in this playlist. But this playlist I will say is very nice playlist for DFS and BFS. Those who have watched it, they can definitely vouch that this is I mean very conceptual playlist that I have created for DFS and BFS particularly. Yes, there is one video here that is for Digestra. If you want to watch a Digestra algorithm, then you will never have to, by heart the Digestra algorithm after watching this video. You will get to know that why this algorithm is working and why this is not working for the negative edges and why it is working for the positive edges. So I have given the proof here in the Digestra algorithm. And similarly, for the merge sort also, I have given iterative merge sort and 5 methods, okay? 5 methods to merge k-sorted k-sorted list into one. So this is, these two videos are very nice. Although these two videos are not related to BFS, DFS, but these two videos are very nice. This video is very, very good, extremely good videos, good video for the minimum spanning tree. So do you know, like in the graph, sometimes they ask like if the graph is given, sometimes they ask that okay, this x is in minimum spanning tree, then what should be the value of this x? Something like this they ask in xyz. So I have solved many good questions related to minimum spanning tree, one or two TIFR question which are very, very good. So this video for the minimum spanning tree is too much good, and the remaining videos that I'm showing here, just 4 or 5 videos that are for BFS and DFS. So I must recommend that you watch those videos. Okay. Although today we are going to solve data structures PYQ, but tomorrow or maybe day after tomorrow we will be solving algo PYQs. But I will not be covering DFS BFS because it will be just a redundant thing, right? It will be just a redundant for me. So that is why I will not be covering, because it is already covered. Okay, let's just get started. So Ratul is saying that please solve hashing PYQs. So we will be solving hashing PYQs also, and coincidences like that we are starting with the hashing PYQ only. Okay. So as I said, like I will be solving good PYQs in this particular session. So let's just get started with this particular PYQ, which is saying consider a hash table. Sorry, actually my I'm having a little bit of cough, so my throat is not that much good. But I hope that you are not getting irritated with my voice. So like I'm not able to speak softly. This is how I'm able to speak, and I don't want to cancel. I didn't want to cancel this marathon, so that's why I've taken it. Okay, cool. Let's just continue. So what they are saying is that consider a hash table with 100 slots. Collisions are resolved using chaining. Okay, so they are using chaining, which means that if there is a hash table, in the hash table, what we are doing, if there is a collision, let's suppose two items are mapping here, then I am doing the chaining here, right? This is what chaining means. Assume that simple uniform hashing is used. Simple uniform hashing means that for every key, I have uniform probability to map it anywhere. That's called simple uniform hashing. Now, what is the probability that first 3 slots are unfilled after first 3 stations? So they are saying that first 3 slots, which means 1, 2, 3, these are the first 3 slots should be unfilled after first 3 iterations. So what is the probability? It means that they are saying that if you are talking about this hash table, then 1, 2, 3. then these 3 slots should be unfilled. You can fill any of this. You can fill any of this 97 slots. Like, I don't care about it. They are saying these should remain unfilled. Unfilled. This should remain unfilled after first 3 insertions. Okay. So let's just do it step by step. Tell me that if you want to remain remain them unfilled after one insertion, then what is the probability? It means you should be mapping your key to these 97 slots, right? Any of this 97. So what is the probability that after one insertion, these 3 slots remain empty? What do you think? What should be the answer? So the answer is that I will be mapping to these 97 slots. Then only these 3 slots can remain unfilled. Then it means that the probability is 97 divided by 100. Very easy. How we are finding this probability? Because this is simple uniform hashing and every slot is equally likely. So I want to fill in these 97 slots. So the combined probability is 97 upon 100, right? So after one insertion, 3 slots remain empty is this probability. Now tell me after 2 insertions, okay, after 2 insertions, these slots remain empty. What is the probability? Now, if I just ask you the same thing and I say that after 2 insertions, it means that it should be remain empty after first insertion and it should remain empty after the second insertion also. Then only I can say after 2 insertions, it will these slots will remain empty. It means these slots will remain empty after first insertion. This is the probability, and should remain empty after the second insertion also, right? And if I just ask you that what is the probability that these slots remain unfilled after the 3 insertions, then you will say it should be remain empty after first insertion, second insertion, and third insertion also, right? So this is the probability by which these 3 slots will remain empty after the 3 insertions, right? I hope you understood this. That was one easy question to start with. Let me know if there is any doubt. Now let me ask you a question that where do we have this information? Where do we have used this information of chaining, that they are using chaining? Have we used this information somewhere? Let me know. Let me know what do you think. Do we have used this information somewhere? The answer is yes. How? See, we do not need to take care about that these things. That okay, what if? See, we do not need to take care about these things in the chaining. That what if after first insertion, let's suppose these are the three slots that I'm looking for, and after first insertion, let's suppose this is the last slot. After first insertion, I'm saying that I can fill, I can go to any of these 97 slots, right? After first insertion, what if I go here? That's not a problem. But in the second insertion, what if I go here again? Right? And if I go here again, then automatically this is going to get filled. So these things I do not need to take care in case of chaining, because in case of linear probing on these things, like other things become very tricky, right? I mean, you should not be going here also. Why? Because if you in the second insertion you go here, like you need to take a cases, like in the first insertion you should not be going, if you go here, like there will be a case in the first insertion, if you go in this key, in this slot, then in the second insertion if you go also in this slot, and so on. Like there might be multiple cases, and this problem could be very very hectic, very very cumbersome if this is linear probing, right? So since this is just chaining, that's why I do not need to take care of these things. Cool. Let's just move to a little nicer problem in hashing, which has been asked in GATE 1997. This is very very nice problem. As far as I know, this is the only good problem that they've asked in the hashing. With respect to the probability. And there are other questions that we will be doing, but with respect to probability, they have asked this as a very good question. So we will be solving that question. And also in the Go classes course, definitely we have done some other probability related questions, and in the test series also you must have find some other probability related question. So there is one subject wise or topic wise test in the algorithm or the data structure. In the data structure, there is some topic wise test that is called hashing. Okay, hashing with probability, basically hashing with probability. So in that test, I think I have put 20 or 25 questions probably. and all of the questions are dealing with the hashing and the probability. So if you want, you can definitely attempt that particular test also, right? That will be helpful to you if you want. Otherwise, that's okay, not an issue. Cool. Let's just continue. So what this problem is saying, is that consider a hash table with n buckets. External overflow chaining is used to resolve the collision. See, again, they are saying the chaining is used to resolve the collision. That makes our life little simpler, right? Because I do not need to take care of the effect of first insertion to the second insertion. Like I do not need to take care. Okay, what if it gets it get map here, and the again should not be mapping here, because if it get map here, then it means that it is mapping to the next slot, something like this, right? So chaining is little nicer for me to solve the questions. Cool. Now, what they are saying, the hashing function is such that the probability that a key value is passed to a particular bucket is 1 by n. What is the n here? N is the number of buckets. So what is they saying, that if n is the number of bucket, if any key is coming to you, that goes to one of the slot, the probability is 1 by n, right? Now let's just see what else they have given to us. They are saying the hash function is such that, okay, that is fine. The hash table is initially empty and k distinct value they want to insert. So number of keys they want to insert is basically k, right? Capital K. And n is the slots. N is number of slots. Now let's do each question one by one, what they have asked. And there are three parts basically here, A, B, C. So let's just do each one by one, what they have asked in A, what they have asked in B, right? Okay. So let me just see that what they have asked in A. A is saying that what is the probability that bucket number 1 will be empty after k insertions. So kth insertion, right? Now you have to understand this very carefully, and before that maybe I can just recap you that what we have done in this question. So whenever they are saying that it should be remain unfilled after first 3 insertions, so whenever I'm going for first 3 insertion and all, so in all of these cases I first show you after first insertion what is going to happen. So I'm going step by step, right? So you have to consider everything step by step. That's the only way to solve these kind of questions, right? Okay. Let me see if there is any doubt. Rohit is saying, okay. Rahil is saying, sir, ये आज का first marathon. Yes, it is the first marathon. I never focused on this point before today. Okay, Vishnu. So Vishnu might be talking about the chaining and all. Cool. They have given the chaining. So I think he just saying that in case of chaining we are doing this question. You have never focused. No problem. So now you know, right? Okay. Now. Yeah, thank you, Vishnu. So Vaishnavi is saying, sir, I'm not able to score good marks in mock. A lot of hard work I did. Everything subject wise, test topic wise. Okay, still not working. Okay, I will, please just ask me this question at the end of the session. I will definitely address this. Okay, so just stay here and ask me this question at the end of the session, because otherwise it will just break the flow. So let's just get continue. Now they are saying what is the probability that after probability that bucket number 1 is empty after k insertions, right? So let's just pick bucket number 1. The similar question we have done just now. They have said like after 3 insertions of top 3 remain unfilled, something like this. So bucket number 1 remain unfilled after first insertion. What is the probability? The probability is that what is the remaining here is n minus 1, right? So after first insertion, after first it get remain empty is basically it means it is as good as saying that you are mapping to any of this n minus 1. So this is the probability that you are mapping any of this to any of this n minus 1. Now after second insertion, what is the probability that it get remain empty after the second insertion? Again, you can map to any of this n minus 1, right? So n minus 1 upon n. So this is the probability that after second insertion, this will be this will remain empty, right? I mean, this particular slot will remain empty. Okay, my mouse cursor might not be shown, so that's why I will be just drawing the images. So this particular slot I'm talking about. So after second insertion, this is the probability that this will get remain empty. But let me know if that is perfectly correct or there is something wrong with this. This is the probability that at the second insertion, right? Not after second insertion. If you want after second insertion, it means after first insertion it should be remain empty into multiply by end because everything is independent, so I can just take I can just do the multiplication, which means probability of after first insertion, let's suppose it is a, and after second insertion it is b, and since the mapping is independent, so that's why you can say that pa into pb. Why I'm saying mapping is independent? Because it does not matter where you have mapped earlier for the second key, right? So the probability is independent. So anyway, like that's how you are writing that after second insertion it remain empty is n minus 1 upon n minus 1 upon n into n minus 1 upon n. Similarly, after third insertion it remain empty. It is basically n minus 1 upon n cube. Right? So that was just easy question. That's the same question that we have just solved. Okay. They are asking for the kth insertion, so you can say k. After kth insertion, so you can say k. The same question that we have done just now, right? Let me know if that is clear or there is some doubt. See, this is the answer that we are getting. Okay, now let's go to this B part. What they are saying in the B is that what is the probability that there is no collision that has occurred in any of the K insertions? Okay, so let me just copy this. Just a second. So what is the probability that no collision has occurred in any of the K insertion? Well, this is a good question. Let's just break this question. Instead of K insertions, let's just break this question into part. So let's just first understand for K equal to 1, then K equal to 2, then we will generalizing this, right? So what is the probability that no collision has occurred in the first insertion? So what is the probability that no collision in first insertion? What do you think? What is the probability? See, there are n slots, right? There are n slots. They are saying that no collision in first insertion. What is the probability? It is 1, right? I mean, there cannot be any collision. So by default, it is true. It is always true that no collision in first insertion, right? So that's why the probability is 1. Okay, cool. Now let's just go to the k equal to 2, which means the probability that no collision in second insertion. What do you think? What is the probability here? Now, just notice that no collision in second insertion means that you are inserting, or I mean, no collision in second insertion, any of the second insertion. So, which means no collision in first and no collision in second. So, first there is no collision, the probability is 1, and then the second there is no collision. Let's suppose the first is mapping here. In the second there will be no collision. What is the probability? It should map to 1 to n minus 1, right? It should be mapping to n minus 1 upon n. So, this is the probability that no collision in any of the second insertion. I mean, neither in the first nor in the second. No collision in the first into no collision in the second. So that's the probability, right? So let's just continue this particular pattern, and let's just see what's going to happen for 3, and then for 4, and then we will be coming to some general idea, which is k. So now what is the probability that no collision in any of the third insertions, 3 insertions basically? It means there should no collision in the first. Anyway, there is no collision in the first. There is no collision in the second. And then when you are inserting the third, then also there is no collision. So what is the probability? This is the probability, because it should not be colliding with any of this. Let me know if that is clear to everyone. That if you are inserting the third one, then also there should not be any collision. So that's how you can solve this question. I mean, for the k equal to 3. Now, what is the probability? Probability that no collision in fourth insertion. What do you think? No collision in, okay, let's not worry about the first, because anyway there is no collision in first. No collision in second, right? No collision in second. No collision in third. No collision in third means that the third key, okay, should not be, like while you are inserting the third key, it should not be colliding with any of these two, which means this is the probability. While you are inserting the fourth key, it should not be colliding any of these 3, right? So this is the probability, right? Okay. I hope you understood. Now, this is the pattern that we are getting. Now, just tell me what is the probability probability that no collision in kth insertion. Now I think you can find the pattern. The pattern is n minus 1 to n minus 2 to n minus 3. If it is 4, then till 3. If it is k, then till k minus 1, right? So you should be writing something like this. The answer is n minus 1 upon n into n minus 1 upon n minus 2 upon n into n minus 3 upon n into, if it is k, then you need to write k minus 1, right? So this is the probability that there will not be any collision in k insertion. But here the k has some bound, which means you cannot say, I mean that's correct, but there is some bound that I need to put on k. For example, let me tell you what is that need. For example, let me just ask you one question. Probability that no collision in any of, if there are n slots, okay, if there are n slots, then any of n plus 10 insertions. What is the probability? If I insert n plus 10 keys, then there should not be any collision, which means k equal to n plus 10. I mean, I'm just putting k equal to n plus 10. Can anyone tell me what is the probability that there should not be any collision in n plus 10 insertions? See, I'm saying that there should be no collision in any of the n plus 10 and n plus 10 insertion. Is this even possible? That you have n slots here, you have n slots here. I'm saying that there should not be any collision in n plus 10 insertion. See, at most n insertion there is some probability. By some you can say, okay, you map it here, you map it here, like that. By some probability you can say that, okay, that there will be no collision if k is less than or equal to n, right? I mean, if you are inserting the keys which is up to n, then there is a probability that there is no collision. I'm not saying that there will be no collision. See, what I'm saying, that if there is a hash table, right? If there is a hash table, then if I insert, let's suppose these are 100 slots. If I insert, let's suppose 100 keys, then I'm not saying that these 100 keys, if you insert here, that will not have any collision. I'm not saying it. What I'm saying is that there is some non-zero probability, or to simplify it, there is some probability by which that these 100 keys will not be having any collision, right? There is some probability basically, right, by which these 100 keys will not be having any collision. Why? Because maybe with some probability it will go here, first key will go here, second key will go here, third key will go here, fourth key will go here, fifth key will go here. I mean, they are going to different slots, right? Maybe there is some probability, at least. This is what I'm saying, right? So if you are inserting 100 keys, then what is the probability there is no collision? Then maybe you can use that formula, that there is no collision in the second insertion. It is this. There is no collision in third insertion. It is this. And if you are asking about k insertions, then it is this. And if k value is 100, then you can just put the 100. Then you will say that if k value is 100, then it is 99. K minus 1 is 99. So there is no collision in 100 insertions. Then you will be saying that this is the probability. Maybe this probability is very less, right? I mean, I don't care about it. But yeah, I'm just saying that there is some non-zero probability. Okay, maybe this probability is very less. Okay, I think it will be very less, because this number is less than 1, right? I mean, n minus 1 upon 1, this is a fractional number. This is a fraction, obviously, because it is a probability, so it has to be fractional number, right? Individual things are also probability. So this number maybe very less than 1. Okay, very less number. Let's not worry about it. But yeah, there is some non-zero probability. At least mathematics is not denying me that there will be a collision or no collision. I mean, mathematics is saying, according to mathematics, I can say that there will be no collision with this probability, right? But if you have the scenario different, where you have 101 keys, then even mathematics will say that if you have even 101 keys, then there will be no collision. ये तो हो ही नहीं सकता कि collision हो ही नहीं 101 keys में भी, 100 ही slots है ना, so there must be collision, right? There must be collision in some of the keys. Maybe I'm not saying that the collision will be at the last. Maybe the collision in the first 2 keys only. Okay, the first 2 keys are having collision, or maybe first 3 keys are having collision, and they are making a chain. And then rest of them are not having collision. That's fine. I mean, using the pigeonhole also you can say. So basically what I'm saying, that if you are inserting 100 keys, then definitely there will be a collision, right? Now this formula, whatever I'm talking about, that there will be no collision after k insertions, it is basically as long as you have at most n. But if you go beyond n, then it will be 0. So that's why I can say that that maybe I can just copy it. Okay. So probability no collision in k insertions. This is this if k is less than or equal to n. Similarly, it will be equal to 0. It is equal to this if k is less than or equal to n. Similarly, it will be equal to 0 if k is greater than n. Right. So I hope that is fine to everyone. Let me know if this thing is clear. Cool. Let's move further. Now let's see what they have asked as a C part. Now what they are saying is that what is the probability that first collision occurs at kth insertion? Okay. See, earlier they were saying that there is no collision in any of the k insertions. Now what they're saying, what is the probability that first collision occur at kth insertion? I think this is also easy. Can you relate these two? Can you relate these two? Suppose you know the answer of B. Can you somehow help me in the answer of C? They are saying that suppose I say that P is the probability. P is the probability that the collision, there is no collision in k insertions. I give you that P is the probability. I mean, let's suppose Pk is the probability that there is no collision in k insertions. And I ask you that what is the probability that first collision occur at kth insertion? So you will say the probability is same as the probability that no collision in k minus 1, no collision in any of the k minus 1 insertions, basically, right? In any of the k minus 1 insertions, any of k minus 1 insertions into the collision that insertion, there is a into the probability that there is a collision at kth insertion, right? The probability that collision at kth insertion. So basically, suppose if I know the answer of this, which is Pk, then probability in that there is no collision in any of the k minus 1 insertions, which is Pk minus 1, if this is Pk, into there is some probability. Okay, let's not do using this method. I don't want to do using this method. I just want to tell you that, yeah, these two questions are related. So let's just do as a fresh question. Okay, let's just see it step by step, that how this C can be calculated. Cool. Okay. So what they are asking is that what is the probability that the first collision occurs at kth insertion? So what does this mean? Let's just maybe let's just break this down by one. Maybe the first collision. Let's just ask what is the probability that first collision occurs. First collision, okay. First collision occurs at first anyway. Like the probability is 0. The collision cannot occur at the first insertion. So at the second insertion, right? So what do you think? What is the probability? The first collision will be occurring at the second insertion. Oh, that question was very nice. I forgot to take that question. I can take that. GATE 2022 question. I answered that on GATEOverflow. That was very nice question in the sense that that could have been solved using 3-4 methods. Have you seen my answer on GATEOverflow on GATE 2022 hashing question? Maybe I can solve it tomorrow. I have not taken that in the slide. I do not have that screenshot, or I can take the screenshot now. Okay. So tell me what is the probability that first collision occurs at the second insertion. Now it is I think easy. What you will say? You will say that at the second insertion the situation is this: there is a key here and you are going to insert I mean, this is the second insertion that you are going to do. You are going to insert something in the hash table. So what is the probability it will map here? The probability is 1 by n, right? So this is the probability that it will map here. Now let me just ask you that what is the probability that the first collision, okay, the first collision is important, happens at the third insertion. What is the probability that first collision happens at the third insertion? It means that no collision should occur at the second insertion. I mean, first insertion anyway no collision will occur. That's anyway true, right? So no collision should be occurring at the second insertion. Second insertion means like you have the one key here, right? So no collision should occur here, which means the probability is that n minus 1 upon n, no collision should occur at the second insertion, and there is a collision at the third insertion. It means the probability third insertion means you have two keys somewhere in the hash table. So this is the third insertion, and there must be a collision in the third insertion. It means that you have two keys here, and and there must be a collision, then what does this mean? That it can map to, let me know what is the answer here. It can map to any of these two, right? 2 upon n. So this is the probability that there is a first collision at the third insertion, because no collision in the second insertion. Anyway, there is no collision in the first insertion. I mean, that's the one probability. There is no collision in the first insertion anyway. There is no collision in the second insertion, and there is a collision in the third insertion. So that is why this is a probability, right? Okay. Okay. Cool. So let's just extend this question. Instead of saying the no collision in the third, I mean the first collision is in the third insertion. Let's just say that first collision in the fourth insertion. Then what does this mean? That it means that there should not be any collision. There should not be any collision in the first insertion. That is true. There should not be any collision in the second insertion, right? Which means n minus. Okay, there should not be any collision in the second insertion, which means n minus 1 upon n. With this probability, there will not be any collision in the second insertion, isn't it? And then there should not be any collision in the third insertion. Third insertion means you have two keys already. There should not be any collision in the third insertion, which means that n minus 2 upon n, and there is a collision in the fourth insertion, right? Fourth insertion means you have three keys already. So this is the fourth insertion. So there is a collision in the fourth insertion means 3 upon n, right? Let me know if that is clear to everyone. So let's just generalize this quickly. Now I said like probability that no collision, sorry, first collision in second insertion, right? What is that probability? Let's just quickly write it. And the collision in the first collision in the third insertion, first collision in the fourth insertion, like that, right? Let's just write these three numbers quickly. So this was the probability. The first collision happening in the second insertion means like okay, then it means n minus 1 upon n, right? And now they are saying first collision in the third, and the first collision in the fourth. So what is the probability that first collision will be in the third? It means there is no collision in the first, no collision in the second, which means what is the probability that there is no collision in the second? Sorry, this is 1 by n. This is 1 by n, right? Okay. Let me know if you are getting me. Now, what is the probability that there is a no collision in the second? It means that the second that this is having one key. Second, no collision means that it should be mapping to remaining n minus 1, and there is a collision, which means out of these two it should be mapping to one of them, so 2 by n. So there should not be no collision in the first, no collision in the second, which means no collision in the second means it should be mapping to n minus 1. No collision in the third, it should be mapping to remaining n minus 2, and there is a collision in the fourth, which means these are the three keys that you have, it should be mapping to one of them, right? So this is the these are the probabilities that we have here. Now let's just quickly generalize this and let's just wrap up this question. Okay, so I have taken only tough PYQs, as I said. So you might feel that things are little tricky here. I intentionally taken tough PYQs because this way you will be learning more, and maybe in for the trivial PYQs you might have already done, right? So I have intentionally taken these kind of PYQs. Okay. Now let's just continue. So what I was saying, let's just continue for the general thing, right? So the probability that first collision in kth insertion, then you will say that see, if it is 4, then 1, 2, and then finally you have 3, right? If it is 3, then you have I mean you have only 1. So if it is, let's suppose if it is 5, then you will be writing no collision in the second, no collision in the third, no collision in the fourth, and there is a collision in the fifth, which means 4 keys must be there. There is a collision in the fifth, right? So something like this. So if it is k, then you will be writing n minus 1 upon n into n minus 2 upon n into n minus 3 upon n. Similarly, if it is by 5, then you have written till 3, and then k minus 1, something like this, right? So similarly n minus k minus 2, till k minus 2 you will be writing into, at last you write k minus 1 upon n, right? Something like this. Let me know if that is okay to everyone. So I am just generalizing the thing. Okay, so for 5, for k equal to 5, I mean I'm writing something like this. So for general k I will be writing something like this. So this is the probability that there is no collision, sorry, there is a first collision in kth insertion, right? Okay, so this is the probability that there is a first collision in kth insertion. Now let's just see something. So this is what we have derived. Now tell me what should be the bound on k. Okay, so let's suppose I say that what is the probability that there is first collision in n plus 20th insertion. Is this even possible that you will be having first collision in n plus 20? No, right? I mean the probability that first collision in n plus 20, then the probability is 0. Why? Because you will not be having the first collision in n plus 20. You will definitely be having the first collision somewhere earlier than n plus 20. So at most you can have the first collision, in the best case you can have the first collision at which insertion? At n plus 1th insertion, right? So this k will be bounded by k is less than or equal to n plus 1. If k is greater than n plus 1, then the probability is 0. Okay, if k is greater than n plus 1. Cool. So I hope you understood this. Now let's just see the answer. Yeah, if k is greater than n plus 1, the, the probability is 0, and otherwise these are the probabilities, right? If k equal to n plus 1, then if you put here n plus 1, then you will be getting something like this. So what does this mean? That let's suppose if I write this thing, that the first collision is occurring. What is the probability that first collision is occurring n plus 1? Sorry. So suppose, let me just copy this. Let's understand this line, that what does this mean to say that first collision is occurring at n plus 1. So what do you think? See, it means there are n slots and each of them are filled, and no, till now there is no collision, and this case coming, then they are asking that what is the probability that this is the first collision in n plus 1. Shouldn't it be 1? I mean, shouldn't the probability be 1, that there will be always uh, a collision at the n plus 1? Shouldn't it be 1? No, right? I mean, they're saying that there should be first collision at n plus 1. It means that it need not to be 1. I mean, at n plus 1, it is not necessary that that there will be a collision. Like, it is not necessary. It is necessary only when there is no collision till now, right? So if there is no collision till now, with this probability there is no collision till now, then only at last there will definitely be a collision. That's why it is 1, right? So if there is no collision till now, then only you can say. So basically, the conditional probability, you can say that given that no collision in first n insertions, right? And what is the probability that collision at n plus 1th insertion? So suppose they give you, then this quantity, if they ask you this quantity, then this quantity is 1, right? Why? Because they are saying if there is no collision till now, it means everyone is full, everyone is filled, and then they are saying collision at n plus 1 insertion. So definitely there will be a collision at n plus 1 insertion, right? So this conditional probability becomes 1. Cool. I hope you understood this question. Okay. Let me move further now. So there are many questions that we have taken. Now let me tell you, basically we will be solving some tree questions. Okay, AVL tree questions, you will be getting some insights of AVL tree. You will be definitely getting some insights of binary search tree that you might not have ever got that kind of insight probably. Okay, and yeah, BST, AVL trees, these kind of questions. We will be solving linked list question. Stack and queue questions I have, but most probably we will not be getting time for that. I mean, I have in the slide. If I have the time, then I will definitely be solving. And mostly we will be focusing on linked list, AVL trees, and BSTs here. Okay. So there are very nice questions that I have taken from previous year questions. So let's just solve them. Again, this is a hashing question. So let's just solve this hashing question once. I mean, this is another kind of hashing question. So let's just solve what they're asking. They're saying a hash table of length 10 with open addressing. Open addressing means that you resolve the collision by open addressing, which means like you go to the next slot. Okay, and there are different methods. Like there is a double hash function, there is a linear probing, and so on. Right? They are saying that they have used the linear probing, and the hash function that they have used is k mod 10. After inserting 6 values into empty hash table, the table is shown below. Okay, so into empty hash table, after inserting six elements, this is the table that we are getting. Now what they are asking, how many different insertion sequence of the key value using the same hash function and linear probing will result in the hash table shown above, which means that if this is the hash table, then what kind of insertion that you must have done, and how many such insertions are possible such that you get this hash table. For example, that if you insert 42, then you insert 23, then you insert 34, then you insert maybe 52, then you insert 46, then you insert 33, then you will be definitely getting this table. How? 43, if you insert, it will map here, 23 will map here, 34 will map here, and 52 will map to 2, but because of linear probing, it will go to 5, right? Something like this. So this is one of the insertion that is possible. But is this the only one? May not be, right? I mean, you may definitely flip these two, and then you can say that there is another insertion using which you can get the same table, something like this. So you can say there is another insertion using which you can get the same table. So similarly, there are many such sequences using which you can get the same hash table, and they are asking about such total sequences that are possible. Okay, so let's just see that how to solve this question. So what do I have? I do have this, and then what we will be doing? We will be checking that okay, this 42 will map where, okay, or maybe in other words, like to which what are the all the keys which are mapping to 2, what are the all the keys which are mapping to 3, what are the all the keys which are mapping to 4, okay, and I think to 4, and nothing is mapping to 5, and to 6 this is mapping, right? So what are the all the keys? Let me know which are mapping to 2. I think 42 will map to 2 and 52 will map to 2, and which are mapping to 3. I think 23 will map, and then 23 will map, and then 33 will map, and for 4, 34 will map, and I think that's all. For 6, 46 will map, right? 1 2 3 4 5 6, 1 2 3 4 5 6. Yeah, these are the 6 keys, and these will be mapping like this. Now check here that let me know if you are convinced with this, that this 23 and 52, let me know if you think that there should be any relationship between these two, which means that what do you think, that 23 should be coming before 52, or 52 should be coming before 22, something like this. So it will depend on the hash table. But one thing is for sure, that this 42 must be coming before 52, which means that if I write the topological arrows, then I must say that this 52 must come after 42. Reason being is that this 42 is mapping to 2, so that's why first 42 is coming, and then 52 might come later. Similarly, if you see 3, then you will say 23 must be coming before 33, right? So if you write 33, then you will say that 23 must be coming before 33. Now, similarly for similarly for 4, it is okay because there are not multiple keys. For 6, there are not multiple keys. Cool. Now let's just see. I mean, this is some small dependency that we have made, but let's just see if we can draw some other dependencies and which are necessary also. So 42 can come before 52. That is fine. Now should 42 be coming before or after any of this? I mean, it should be coming before 52. Apart from 52, let's suppose 52 is not there. Should it be coming before 23? I don't think there should be any relationship, right? I mean, 23, 42, there is independent. They can come at any time. Similarly, 34, 42 independent. 42, 52. Okay, that's what we have already captured. 42, 46, I think independent, because 42 can come before, 46 can come after. Nothing will matter. And 33 and 42. Okay, with respect to 42, I don't think it will matter. If 42 comes first or 33 comes first, I mean, the 42 is anyway going to map here only, right? Even if 42 comes later than 33, isn't it? See, if 33 is coming, maybe let's suppose that 33 is coming before 42 or 42 is coming before 32. So if 42 is coming before, then 42 will map here. If let's suppose 33 is coming first, right? Yeah, one thing is sure, but that 33 should be coming after 52. That is for sure. So basically, let me make it simple. That you see here, this 33, that is hitting this and these. I mean, this 1, 2, 3, 4. So it is basically getting collision with 1, 2, 3, 4. So that's why. And 33 is not it is not it at its own place. It is getting collided with these 4. So it should be coming after these 4. So 23, 34, 52, 46. So maybe you can say this 33 should be coming after all of them. I mean, see, it is getting collide. You should be seeing that it is getting collision with how many keys? It is getting collision with all of the keys, right? Apart from this 42. But yeah, it should be coming after the 52, after any of this, right? So it should be coming after 52. It should be coming after 23, and it should be coming after any of this, which is 34 and 46. So these are 1, 2, 3, 4. It should be coming after 34 and 46. So let me write here 34 and 46. So it should be coming after 34 and 46, because it is getting collision with all. Now this 42 is not getting collision, and 52, let's see, the 52 is getting collision with whom? 52 is getting collision with 1, 2, 3. So that's why it should be coming after these three, right? 42, 23 and 34. 42, 23, 23 and 34 also. So 52 should be coming after all of this, because 52 is getting collision with these things. Now 23 will be coming here, and then 33 has, okay, 33 is done. 33 is getting collision with these all. 34 is not getting any collision. I mean, 34 can come directly, because these slots are very simplified. 4 and 6, they are saying that for 4 and 6 there are just these are the individual numbers which are mapping to 4 and 6. So this 34 can come, I mean, as long as I'm capturing the other dependencies, so 34 can come. I mean, there are no additional dependency on the 34. Similarly for the 46. So basically how we are drawing this graph is seeing that which key. So key, for example, 33, it is getting collide with how many? So it should be coming after all. This 52 is getting collision with these three. So that's why this 52 should be coming after these three. 33 is getting collision with these four. So 33 should be coming after these three, these 3, 4, whatever, right? And similarly, like, I mean, I have drawn the dependency based on that it is getting collision with whom. So 33 is getting collision with all. 52 is getting collision with how many? Similarly, I can say 42 is not getting any collision. So 42 should be coming first. Basically, it is not like it can come later. Since it is not getting any collision, so it must be coming before 52, right? Because it is not getting collide with 52. So anyway, you when you write the keys which are getting the collision, which means the 33 and 52, then almost everything is sorted, right? See, let me let me go to the next page. Let me just try doing it again based on the intuition that we have just driven. So basically, let's just see that this 52, since this 52 is getting collision with three keys which are 42, 42, 23 and 34, right? 23 and 34, which is 52. So 52 is getting collided with three keys, right? So that's why it should definitely be coming after these three. So that's why I'm putting these arrows, right? Okay. Now, what is next? Next is 33, which is getting collide with 23, 34, 52, 46. So 33, it is getting collide with 23, 34, 52 and 46, right? 46. Cool. So I have written these two, and now let's just check if I'm done. So let's just check if I have something else. So this 42 must be coming before 52. I have captured it because of the 52, right? I mean, whatever 52 dependencies, either after it or before it, I have captured it. I mean, at least see, before 52 I have captured, and before 33 I have captured. After 52, what is coming? I have not captured. Probably I need to capture. So okay. So let's just see. So after 52 I have not captured, but before 33 I have captured. That is coming, I mean, that is already capturing one dependency, which is basically 52 33. So this is covered. So what I'm saying here, that before 52 whatever is there I have captured, before 33 whatever is there I have captured. So I have captured only two things. Now I need to check that this 42, right? So let's just do one thing. Let's just let's just go for before only, okay? Because after dependency which automatically be covered. So before 42 what should be coming? Tell me. Nothing, right? So that's why, I mean, there is no dependency on 42. I mean, there can be, but there is no forced dependency basically. So let's just capture only before dependencies. Let's just capture only before dependencies. So before this 42 there is no dependency that it have to be coming. It's not like that, right? So before 52 I have captured all, before 33 I have captured all, before 23 let's just see. So before 23 there is no dependency, right? Because 23 can come, and before there is no necessity that 42 to come or 42 to come after that. I mean, before there is no necessity. Similarly, for 34 there is no necessity before, right? Or there is necessity. I mean, before 34, should I be saying that something should definitely be coming? Then only 34 will be at this location? No, because 34 is at its correct location. So before 34, like, I do not have to have anything. There might be something. There might be these things, but I do not need to care about it. Like, I mean, what I'm saying, that what is forced before 34? So is there anything that is forced before 34? No, right? If that is mapping to its own slot, then there is nothing that is forced, right, before that. So there can come some things. So if something is mapping to its own slot, then there should not be anything forced that, okay, this should be coming before it, right? See, if 33 is not mapping to its own slot, then these things should be coming before. Okay, so let's just capture only before things. So there is no dependency for 42, before no dependency, because it's mapping to its own slot. No dependency on 23 before, because it's mapping to its own slot. Before no dependencies, right? Yes, there are before dependencies for 52. There is before dependency for 33, and that's what we have captured. So this is the graph that we are getting. Let me know if that is fine to everyone. Okay, so maybe before I solve this question, okay, so this is the graph that we are getting. Before I go and find out the all topological sort for this particular question, let's just do one more practice problem, and let's just see if we can draw a dependency graph or a topological graph, or the dependency graph for that, and then we can find the topological sort or not. So let's just do one more problem. That problem I have given in data structure test, that hashing test. In that test I have given this problem. So let's just see if I can draw a dependency graph using just an intuition that we have just drawn. Okay. So let me do one thing. Let me just read out this problem, and let's see what it is saying. Suppose we implement a linear probing with hash function hx equal to x, hx equal to x mod n, right? Mod 9. So that is fine. After inserting 7 keys, the table is shown below. So they are saying that after inserting 7 keys, this is 1, 2, 3, 4, 5, 6, 7, and this is the table that we are getting. Now, how many total insertion orders are possible, okay, to reach the above state of hash table? For example, these are the two possible which are given. I mean, you can insert in this way, maybe 12, 14, 3, 9, like that, or maybe you can insert in this way. And if you insert either in this way or in this way, you will be getting the same hash table. That's what they're asking, that how many total are possible. So let's just see if we can if we can make a dependency graph, then we will be able to solve this question easily, right? So let's just see if the dependency graph is possible. I mean, is easy to write or not. Okay. So for that, what I'm doing, I'm just helping you out with something which is basically I'm just telling you, since you do you need to do mod 9, so that's why I can just help you with the mod. So these are the mod results. Okay, I'm just writing the mod results, which means I'm saying the 9 8 maps to 0. So whoever is mapping to 0, I'm just writing it, and whoever is mapping to other slots, I'm just writing it. Okay, so these keys are mapping to 3, these keys are mapping to 4 and 5. So let's just do this. So 9 8 are mapping to 0. So one thing is for sure that let me just go for the before dependencies. Okay, let me know that if I need to have anything before 9. No, right? Because 9 is mapping to its own slot. Nothing before 9 is compulsory. Let me know if I should be having anything before 18. Yes. See, well, 18 must be colliding with 9. So there must be a dependency before dependency. Something like this, right? This is the before dependency I'm interested in. Now, let's just check if 12 is mapping to its own slot. So there is no before dependency for 12. 3 is mapping to not, I mean, to the different slot that it should map to. Okay. See, this is mod 9. This is not mod 10. Okay. The hash function is mod 9 because there are 9 slots. So this 12 is mapping to its own slot, no before. 3 is not mapping to its own slot. So 3 must be coming before 12. That is for sure. And then 21. 21 is here. 21 must be coming before 12, 3, 14, 4, right? So 21, maybe I can write like this. If it is 21, that must be coming before everything. Before like 21 will be colliding with this. Before 3 it should be coming. Before 14 it should be coming, right? Before 4 it should be coming. 4 maps to its own slot, no worries. And 14 maps to, sorry, 4 maps to 4, and 4 is mapping to actually 6. So it means that 4 must come before 3 and 14, right? So before 3 and 14, 4, sorry, after like 3 and 14 must come before 4, right? 3 and 14 must come before 4 because 4 is 4 should be mapping to 4, but it is mapping to 6, so it is colliding with 3 and 14. So after only 3 and 14, 4 should be coming, right? Okay. 14 maps to 5, so that's fine. There is no before dependency for 14. Okay, let me quickly check if I have captured all. Now 9, there is no before dependency for 9, so I'm not bothered about 9 because it is mapping to its own slot. And 3 is getting mapped to 12, so there should no before for 3. 4 is mapping to, okay, 5 is mapping to 14, so there is no before here. Okay, 18 is not mapping to itself, so 18 must collide with 9. 3 is not mapping to itself, so 3 must collide with 3 maps to 3, so 3 must collide with 12. So 12 should be coming before 3, that is fine. 21 is not mapping to itself, so 21 must collide with every one of this. 12, 3, 14, 4. So 21, 12, 3, okay, 14 and 4 also, right? 21 must be coming after all. And then 4 maps to 4, which means that 4 must collide with 3 and 14. 4 must collide with 3 and 14. Yes, I have captured it. And yeah, so I think that is all right. So this is the graph that we are getting. Let me just check if we are getting the same graph. So they are getting this 9, 9, 18. Let me just copy this. Okay. So they are getting this 9, 18, which I am getting 12, 3, 4, 11. So 12, 3, 4, 21. So basically this is just transitive dependency. If you want, you can just remove this. There is no worries about this, right? Okay. 14. this 21 should be coming, 21 should be coming after 4 and like after 4 and 14, but anyway this is again a transitive dependency. The 21 should be coming after 4, and anyway like 4 should be coming after 14, so that's why this is again a transitive, I mean redundant dependency, so I'm just removing it. Yeah, so simplification is like this, right? I mean earlier also that was fine, but this also it is fine, right? So basically you will be having this dependency graph. Let me know if that is clear to everyone. Let me know if that is clear to everyone. So basically what we are doing, we are just checking if we can make a dependency graph, right? So how we are making a dependency graph? We are just using the before dependencies, and before I'm making sure that what should be coming before it, right? If something is mapping to its own slot, then I do not have to any worry. If it is not mapping to its own slot, right, then I have to see that what should be coming before it. So let me write it here. If some key maps to its own slot, then we are okay. I mean we do not have to write any dependency explicitly. We do not have to worry, right? Okay, is this color okay to everyone? I mean white color or cream color, whatever. So let me write with different color. If some key does not map to its own slot, does not map to its own slot, then we need to check what all should come before it. What all must come, right? These are the only two things that we are doing to draw the dependency graph. Now once you have the dependency graph in place, which is like this, now what we need to do, we need to find all the topological sort, which means that I need to check that how many in how many ways this can occur. So I mean there is no, I don't know, or I think there is no simpler formulation that how to find the topological sort, number of topological sorts. So I mean topological sort, finding topological sort is easy. You can just find the topological sort very easily. I mean using the DFS, if you want you can find. If you know that if I don't know if you know, there is one theorem in the DFS which is basically the topological sort. I mean if you apply the DFS on any edge, then like let's suppose for this graph I want to know the topological sort, then you apply the DFS on it, then tell me what is the finish time of u. I mean if you talk about the finish time, then this finish time, let's suppose it is 1, then this is 2. So basically this finish time must always be, if there is an edge, then the finish time of v, okay, if ub is an edge, then finish time of v must be lesser than finish time of u. Okay, there is one theorem, I mean that's easy to prove. So basically you can find out the finish time, and once you find out the finish time using the DFS, then you can find the topological sort also, because for every edge that is true that finish time of v is lesser, and I want you to be right first in the topological sort, so I will sort in decreasing order of finish time. Decreasing order of finish time. Actually there is some PYQ also based on this particular statement, that how topological sort and DFS finish time are related. Do you remember there is one PYQ? There is one PYQ using on this statement, that how topological sort and DFS finish time are related. So basically for every edge that must be true that V finish time. So if UV is an edge, then if UV is an edge, then B finish time must be lesser than U finish time. Okay. So what we will be doing, we will be applying the DFS, then we will be writing the highest finish time first. Okay, because we are sure that if this is the highest finish time, then there is no edge which is incoming to it, otherwise this will be the higher, right? So we will be writing the highest finish time first. So we will be writing u highest finish time. So basically we will be arranging in order of the decreasing order of the finish time, and that's how we can find out the topological sort using DFS. Anyway, coming to this, so as I said, like you can watch the DFS VFS videos. These are very nice videos. Just watch them. Okay. So coming to this, you need to find the number of topological sorts. So see here, 52 should be coming coming before 42, 23 and 34, right? So sorry, after, right? So 52 is here. Then these are the 3 factorial possibilities by which I can arrange these, right? So using 6 ways I can arrange, and then 52 will be here. Now I need to insert 46 somewhere, right? I mean, then 46 can come. 46 can come anywhere, maybe here, because 46 has no dependency to 52, right? Or it has. See here, the 46 and 52 are not dependent, right? In the topological, in this dependency graph also, it seems like they are not dependent. They can come anywhere, because once these are coming, which means that 52 and 46 are independent. Once this is finished. Okay, so anyway, so basically this 52 and 46 has no dependency. So you can say this 46 can come, these are the six ways. Now 46 can come here, okay, here. So these 3 dots are basically representing one of these 3 numbers, right? Here, or here. So 1, 2, 3, 4, 5. 5 are the positions where the 46 can come. So basically I'm done with these 3. I'm done with 46. I'm done with 52. Now this 33, since it is dependent on all, that's why it must be coming here, right? It must be coming at the last. So there is only one way for 33. So finally answer is 30. I mean, there is no simpler way. You have to use your own intuition to come up with the answer. Okay. Let me know if you have understood. So you can use the discrete mathematics way. Okay, like, I mean, this is not the algorithm or data structure. There is some algorithm using which, or there's some method in the data structure using which you can do it. You have to do it using your own intuition. Let me see if there is any doubt. So someone is asking, why comparing 0 in degree, can we say there are 4 factorial ways? Yes, you can say. I mean, there is no problem. So maybe let me let me have maybe one more way of solving it. I mean, someone is saying that we can have 4 factorial ways. So yeah, so you can do it. I mean, there are multiple ways of solving it. Let me just write it here. So what you can do, you can write the 4 factorial ways in which these 4 can come. That's perfectly sure. But then you have to think that this 52, if you have to arrange this 52, see these 4 factorial ways, let's suppose that these are the 4 dots, which is basically 4 into 3 into 2, which is 24 ways, right? Now, if you have to arrange this 52, then this 52 must be coming before these 3, and it is independent of this 46. So now you have to take the cases. That's why it will be little messy. Like if 46 is this one, or maybe 46 is this one, or maybe 46 is this one, or maybe 46 is this one, right? And then based on that, you can say if 46 is this one, since the 52 has to come after all, then 52 will be coming here. If 46 is this one, then 52 can come maybe. I mean, see what I'm saying. Again, it will be little messy actually, to be honest. But yeah, there are 4 factorial ways. That's fine, but then you have to take the cases. The case one is that this is the case one when 46 is here. If 46 is here, then 52 must be coming. See, 33 is anyway at the last. Okay, so let's talk about the case one. If 46 is here and these 3 dots are representing this one, then 52 must be coming after these 3 dots. So 52 is here only, right? There is only one way in this case. Case 2, where 1, 2, 3, 4. If 46 is this middle one, I mean this one, 46 is this one, then also like this 52 should be coming after these 3. So I think the 52 is only having only one position according to me. So it is 1, right? Okay. So similarly, in the case 3 also, there is only one place where the 52 can come. If 46 is this one also, then also 52 can come here. There is only one case. Case 4, if 46 is at the last, is here, then 52 can come either here or 52 can come here. So these are the 2 possibilities. So this is one possibility where 52 can come, and anyway, like you can basically do these permutations, 3 factorial permutations. So I think you are again end up with the same thing. 2, 3, 4, 5, right? So 5 into 3 factorial. 5 into 3 factorial. So anyway, you have to make the cases and all. You can do in that way. That's not a problem. But then 52 is not having any dependency. So that's why there will be a different cases, right? Okay, cool. Let me know if there is any doubt. You can do that problem, and for the sake of practice you can also do this problem. This problem I have given in one of the test in Go classes. Let me know if you have solved this problem already. This problem I have taken some standard university. I do not remember the name on top of my head, but almost all the problems we take from the standard universities only. So this problem also I have taken from a standard university. Good. Now let's talk about the heap. So we have finished the hashing problems. There was one GATE 2022 problem which is also very easy and very nice problem, because I have also answered that problem, so that is some connection with that particular question. But I will take that question tomorrow, okay? Because I don't have this question currently with me, so I need to search it on all. So I will be taking that question tomorrow. I've answered that already on Geo, and using 2 3 methods I've answered, like different random variables and all. So I really answered it well. You can check that out. But for now, let's just focus on the heap problems. Okay. Yeah. Thank you, Rohit. Now, what they're saying, a min heap with n elements with smallest element at the root. Okay. Obviously, like if it is a min heap, then smallest will be at the root only. The seventh smallest can be found in how much time? That's what they're asking. If it is min heap, then tell me where will be the smallest? Smallest will be on the top, right? So let's suppose that like just for the sake of simplification, I'm taking the numbers 1 2 3 4 5. Does not matter. I mean, you can take any number, does not matter. Just for the sake of simplification, I'm taking 1 2 3 4 5. Okay, there could be the repetitive elements also. There could be 1 1 1 1 1 3 3 5 5, something like this. I mean, there could be anything. You can take any of the case. I will be taking the repetitive case also. I mean, that's not the different case, but anyway, like I will be telling you that it does not matter if the numbers are repeating or not. So tell me what will the root? It must be 1. Then tell me what can come here. What can come here? Which number can come here? If let's suppose there are if the height of this tree, what they have given, the n elements, okay? So if there are n elements and if it is heap, then the height of the tree will be log n, right? Okay. So anyway, so what I'm asking here is that if this is min heap, okay, if this is 1, let's suppose some number is coming here, 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 then tell me whatever number is coming here, whatever number is coming here, since it is min heap, that's why all of these numbers, whatever number is coming here, then let's suppose all of the numbers are distinct. Then tell me, can 2 can come here? Answer is no. Reason being is that this should be in the increasing order. I mean, these numbers should be in the increasing order. Why? Because this is a min heap. So this should be smaller than this. This should be smaller than this. So if you're writing, let's suppose 3, then you can write 4, 5, something like this, right? 4. If you're writing 4 here, then you can write 7, you can write 11 here. That's not an issue. But these numbers should be in the increasing order. That's what I'm saying. Okay. So I hope you understood this. Now, what I'm saying here is that like 2 cannot come here. Reason being is that these numbers Okay, I think now it is resolved. Okay, so let's just continue. What I was saying, I don't know till till which point you have heard me, but anyway, let me just continue. Now, what I was saying, that if you are having any heap, which is, let's suppose this is the heap that you have, the minimum is at the top. My question is that where can be the third smallest? Okay, where can be the third smallest? Third smallest means, like, for the simplicity, I'm taking the example which is 1 2 3 4 5 6 7 8 9 10, right? So third smallest in my case is 3. If I'm taking this example, then third smallest in my case is 3. So where can be this third smallest? Tell me. Can it be here? Can I write 3 here? This is my question. Answer is that I cannot write 3 here, because everything from this root to this point 3 should be in the increasing order. Okay, now is this audio fine? Okay, now I think audio is fine, right? So basically what I'm saying, that uh, okay, cool. Now I think audio is fine. Okay. So what I'm saying, that third smallest, which is 3 in my case, cannot be coming here. Reason being is that if you write 3 here, then everything from root to this point should be in the increasing order, because this is the min heap. So if you're writing minimum here, then you can write anything, but it should be greater than the minimum, right? Obviously, it is, you can write 5 or anything, you can write 3, you can write anything here, right? So let's not worry about it. Let's suppose I'm writing anything here, which is 3. Then again, you should be writing greater than this, right? Greater than 3. You cannot write 2 here now, right? You can write 2, but not here. You can write here, definitely, right? But not here. So basically, in case of heap, there is no relation between the siblings, right? Between the siblings, you do not have any relation. So when we are solving the heap question, we do not need to worry about the sibling relation. There is no relation between the sibling, but there is definitely relation between the ancestor and the descendants, right? So if this is 3, there has to be 4 5 6 anything, right? There has to be 10 or something. I mean, there has to be greater than 3. So similarly, what I'm saying, that if we are writing 3 here, if we are writing, let's suppose, 3 here, then everything from root to this point should be greater than 3, right? If it is greater than 3, right? Sorry, from root to this point should be in the increasing order. I'm sorry about it. It should be in the increasing order, which means that you must be writing something greater than 1 here, right? Which is 2, and then you must be writing something greater than 2 also, but you don't have that, right? So what you will fill here? What you will fill here? See, suppose you are saying that 3 is here. Can 3 be here? This is my question. If 3 is here, then what you will fill here? This you cannot fill this particular slot with anything, right? So 3 cannot be here. Reason being is that from root to this point, everything should be in the increasing order. And if everything should be in the increasing order, then I do have the limited nodes, right? I do have the limited nodes. So I cannot fill this particular slot. So that's why 3, let's suppose this is the level 0, level 1, okay, level 0, level 1, level 2, level 3. 3 cannot be at level 3 or beyond 3, right? So basically, if I say that, let's suppose that if I just ask you, this is 1, okay, 2, 3, 4, 5, 6, 7, okay, 7 can be here, but let's suppose if I just say that can 3 be here, or maybe can 4 be here? Let me ask you, can 4 be here? Then everything should be here in the increasing order, right? But you just have 2 3, and there are so many slots to fill. So 4 cannot be here, right? Can you tell me, if this is level 0, then can 4 be here, can 4 be here, which is level 0, 1 2 3 4 5 6, okay, whatever, right? 1 2 3 4 5 6, yeah, this is level 6. So tell me, can 4 be at level 6? No, right? Because if 4 is here, then you should be filling everything in the increasing order. Then there is just 2 3, just 2 3. These are the two numbers that you have in between. So 4 cannot be here, right? Can we fill it with 2? Which position? So you cannot fill this particular position with 4. Cool. Now tell me, can 4 be at this position? Can 4 be at this position? Tell me, can 4 be at this position? Can 4 be here? Let me know. This is a min heap. Can 4 be here? See, I am saying it cannot be beyond. One thing I am saying that it cannot be beyond the see 1, 2, 3, and 4. 4 can be here at most. It cannot be beyond here, right? I am saying that it cannot be beyond here. This is what I am saying. It cannot be beyond here. One thing I just fixed out. Now I am just asking you the another question, that if 4 cannot be beyond this, can 4 be? Where can 4 be basically before this, right? It cannot be beyond this, but where can 4 be here? This is my question which I'm asking. Let me know. Yeah, most probably it can be here. Why I'm saying most probably? Reason being is that why I'm not saying the 100%, because most probably it can be here. Reason being is that it depends on the number of nodes you have, right? If you have sufficient number of nodes which you can fill, see, let's suppose the height is fixed. If you have let's suppose the sufficient number of nodes, and you have to fill, let's suppose these two, then you should be having enough nodes which are more than 4, which means you should be having 5 and 6 if let's suppose till this point you want to fill the heap. Anyway, let's not worry about it. We will solve one question, from that it will be clear. But yeah, for now, the 4 can be, let's suppose I have the sufficient nodes, so 4 can be anywhere in these nodes, right? In these nodes 4 can be anywhere. 4 can never be at this position or nor at this position. 4 can never be anywhere after it. I mean, anywhere can never be at this. Reason being is that let's suppose 4 is here, then this path must be increasing order, right? This path must be the increasing order. I do not have enough nodes to fill here. I just have 2, 3, right? So that is why 4 cannot be after this level. That is for sure. If 4 has to present, then 4 must be within this level. This level means this is level 0, this is level 1, this is level 2, this is level 3. So 4 must be up to level 3, isn't it? Now similarly, if I just say that, if this is many sorry, if this is many heap, if I just say that this is 1, okay, if I just ask you where can 7 be, so this is 1, this can be 2, 3, 4, 5, 6, 7. Okay, now can 7 be after this position? This is my question. The answer is no, right? 7 cannot be after this position. 7 cannot be here. Reason being is that by chance 7 is here, by chance 7 is here, then you should be having everything in the increasing order. You should be having 2, you can fill with this 2, 3, 4, 5, 6, but one of the slot will get empty, right? So that's why 7 cannot be here. So if 7 has to present, then 7 must be till this point only, right? Okay, let me know if that is fine. So seventh smallest, which is 7 in my case, seventh smallest, which is 7 in my case, because I'm just taking 1, 2, 3, 4, 5, 6, 7, must be here till these levels, till the level 6, which means how many nodes till this level 6? I think till height or level. I mean, I think this is h plus 1 minus 1. So there should be some. This is 6, and there should be, I think, 127 nodes, right? So basically, 7th smallest must be here in this 127 nodes. Let me know if this is clear. If the nodes are distinct, I will tell you. If they are same, then what's going to happen? Okay, I will tell you if they are same, then what will happen? Now, if these are distinct, then 7 cannot be here. Suppose that nodes can also be same. Okay, so I am saying the nodes can also be same. So suppose, so one thing is for sure, that if they are distinct element, then this 7 cannot be present here, right? But am I really interested in 7, or I am interested in 7th smallest? I'm interested in 7th smallest, right? I'm not interested in numbers. I'm interested in 7th smallest. So let me talk about the 7th smallest only. So one thing is for sure, that 7th smallest cannot be. This is level 0, 1, 2, 3, 4, 5, 6. So 7th smallest cannot be after it. One thing that I have just found it out, right? But now you will argue me one thing, that what if nodes are same? Let's suppose that this is 1, 1, 1, 1, everything is same, right? 1, 1, 1, 1, 1. Then 1 can definitely be here, and 1 is the 7th smallest. Okay, are you getting my point? Or maybe let's suppose that 7th smallest itself is repeating. Let's suppose I have the numbers which are 1, 2, 3, 4, 5, 6, 7, and then 7 is coming 2 times. Suppose, for example, then you will say 1 can be here, 2 can be here, 3 can be here, 4 can be here, 5 can be here, 6 can be here, 7 can be here, and 7 can be after this, beyond this level also, right? Beyond this level also 7 is here. But am I really interested in this 7? This is my question. I am interested in 7th smallest. Am I not 100% sure that 7th smallest must be again in this area only? Let me tell you how. See, first you should be convinced if distinct element, then 7 cannot be here because there will be a gap, right? Now let's suppose I have some numbers something like this: 1 1, 2 2, 3 3, 4 4, 5 5, something like this. Okay, suppose I have some numbers which are looking something like this. Tell me what is the minimum number here. Minimum is this is called smallest number here, right? This is called smallest. Tell me what is the largest number here. This is called largest. Tell me the second minimum number here. What is the second minimum? Second minimum is also 1, right? Minimum is 1, second minimum is also 1. This is the second minimum, right? This is the second minimum. So I will say minimum is also 1. Minimum is 1. Second minimum, this is the second minimum. This is the third minimum. This is the fourth minimum is also 2. Fifth minimum is 3. And sixth minimum is 3. And the seventh minimum is 4. Eighth minimum is 4. Ninth minimum is 5. 10th minimum or the largest is also 5. Isn't it? So if I'm interested in the 7th minimum, okay, then there might be multiple copies of the 7th minimum. Okay, or if I'm interested in something, then there might be multiple copies, but one of the copy must be till that point, right? See, I'm 100% sure that from here, this is 1, 2, 3, 4, 5, 6, 7. Okay, so I'm 100% sure that if this is root, okay, this is root, from here to here, everything should be in the increasing order or at least non-decreasing order. Okay, non-decreasing. Non-decreasing means that there could be equal to also, right? So if that has to be in the non-decreasing order, then if this is minimum, then this must be, it could be 1. Numerically, it could be 1, but I don't care. Numerically, it could be 1, but it must be the second minimum also. Numerically, this can also be 1, but this must be the third minimum also. So I don't care if the values are repeating or not. What I care that from here to here, since this is the non-decreasing order, that is 100% sure, right? Then if there are multiple copies, then one of the copy must be here also, or anywhere in this, right? If there are multiple copies, then I do not need to worry about it. Let me know if you have understood this correctly, right? So what I'm saying here is that if 7th smallest you want to know, then 7th smallest is within this boundary. Suppose I contradict myself. Suppose I say that 7th smallest, okay, 7th smallest, I'm not worrying about the numerical value. I'm saying the 7th smallest is not in this boundary. 7th smallest is basically after this boundary. I'm not worried about the number as repeating or not. Okay, so I'm saying in general, I'm saying that 7th, if you are claiming me that 7th smallest need not to be within this boundary, 7th smallest, let's suppose could be here. Okay, it could be here. Let's suppose the 7th smallest is after 8, is here. The first time 7th smallest is appearing, you are saying this is the 7th smallest, which is where the first time it is appearing. Okay, I'm not worrying about the number are repeating or not. Then I will just say that okay, if this is 7th smallest, then let's just find out the path from this to root. There must be some path, whatever that path is, right? There must be some path from this to root, and since this is heap, so you will be saying this path must be in the non-decreasing order. So how can this be the 7th smallest? This is the first smallest for sure, right? If this is 7th smallest, then this cannot be true, okay? Because some, like, there has to be, if you write that in the order, if this is A, this is B, C, D, E, F, G, H, I. If you write A, B, C, D, E, F, G, H, I, this order must be non-decreasing, right? So this is the, I actually do not know, like first smallest, second smallest, I do not know here. I do not know. I need to find out where is the first, or like first smallest I know, but apart from that, I do not know. Let's suppose I do not know, okay? So, but I'm sure that this I cannot be the seventh smallest, because this is, if this is first, second, third, fourth, five, six, seven, seven must be till this point only, right? If this is the first time seventh smallest is coming, then what is this G doing here, right? You're getting my point? Okay. So, dangerous Clady is saying then the second seventh should be in the eighth smallest. Yeah, second seventh should be the eighth smallest, something like this, right? So basically, what I'm saying that seventh smallest has to be here. It can be here also. I'm not denying the fact. See, if there are multiple copies, if everything is having one, okay, if everyone is having one, let's suppose this is the min heap. I don't care, okay? I mean, if everyone is having one, then I'm sure that seventh smallest is here only till this point. Maybe it is here. I do not care. Maybe it is here. I do not know actually. Okay. If there are multiple copies, then maybe it is here also. But one thing I'm sure that it is here also. Okay. This is I'm sure of. So they are saying, let me move further because there are many questions we want to do. They are saying that seventh smallest element can be found in some time. Since I know that seventh smallest has to be found within 127 elements, so that's why this becomes order of one problem only. Okay, that's why D is the correct answer. Let me know if you have understood this. Okay, now let's do this problem. In the binary max heap containing n numbers, if it is a max heap, then smallest element can be found where? So, see, I do not know numbers are repeating or not repeating. Let's not worry about it. They are saying there are n numbers, right? So, the heap looks like this. If it is a max heap, let's suppose this is 100. Then they are asking the minimum number. Tell me, can minimum be here? See, if this is max heap, then from this root to everything, it should be in the decreasing order. If this is 100, then this may be 80, right? It should be in the decreasing order or the non-increasing order. I mean, to be honest, it should be non-decreasing. But let me just write decreasing because it is easy to understand with the decreasing. Okay. I mean, non-increasing and these things are not very much intuitive. So let's suppose this is the decreasing order. So what I'm saying, from root to everything, you go down, everything should be in the decreasing order. Now, I'm just asking you one thing. If this is 100, which is maximum, suppose in my case, then can the minimum be just after this maximum? Can the minimum be here? Just after this maximum. If they are distinct number, let's suppose they are distinct number, or I'm talking about the I mean the minimum, the smallest one, is a distinct number. If minimum is here, since everything should be in the decreasing order, then what you will put here, right? You cannot put anything here. You're getting my point? You cannot put anything here. So that's why minimum cannot be in between. Because let's suppose even if minimum is here, even if minimum is here, then also you will say that what you will put here, because this should be in the decreasing order. Agar let's suppose minimum is 1 and there is no number which is lesser than 1, then can 1 be here? Since you have to put everything in the decreasing order, that's why you cannot put 1 here. Okay. So I hope you are understanding. So basically, minimum must be at the last level, right? If it is a max heap, then I will say minimum must be at the last level. Okay, which means that if that is the case, then minimum, if this is 100, then minimum must be here. Now you might argue that okay, what if elements are repeating and minimum is here? Let's suppose minimum is 7 or minimum is 10 or something. Let's suppose minimum is this, okay, which is minimum, and then you will say that okay, see, minimum is here, and since minimum are there are multiple minimums, and then this is 10 and 10. Does this violate my condition? I am saying that minimum must be here. I am not saying that it cannot be in the between. I do not know. If there are multiple minimum, then maybe it is in the between, right? If there are multiple minimums, then why not? Why not this can be in between? Maybe it is in between if there are multiple minimums. But I am 100% sure that one of the minimum is at the last, right? One of the minimum is at the last, in the last level. Because it should be in the decreasing order. if let's suppose minimum, if there is whatever minimum x, let's suppose there are 10, there are let's suppose 2 minimums you have, okay. If both of the minimums are in between only, there is no minimum at the last, then if both of the minimum are coming here, then this should be these numbers are actually lesser than all the numbers, right? So these among these numbers, there must be minimum. So minimum must be at the last level. It can be in the between also. If minimum is repeating, then it can be in the between. I am not denying this fact. Okay, but it must be at the last level. So if this is the max heap, then I do not have any information about the minimum, unfortunately. It can be anywhere, multiple minimum can be anywhere, but one thing I'm sure, it must be at the last. Okay, so if this is max heap, I do not have any information about the smallest. Only thing I know that must be at the last. Actually, in the Go classes course, I have taken this many cases. I've explained this very nicely, that where can the minimum be, and in the max heap, min heap, everything I've cleared very nicely. I think some of you who has watched the lectures maybe can tell me. Okay, cool. So that's why at the last, since I know that they are saying that these are the n total numbers, at the last approximately half of the things are at the leaf. Okay, these are the n by 2 numbers in the leaf, approximately half of the things, right? So because of this n by 2 numbers at the leaf, that's why I will say this is order of n. So you do not have any other information. That's why this is the correct answer. Okay, cool. Now see, this n by 2 numbers is in the leaf. This thing is so powerful that this has actually helped us to build an algorithm that is called build heap. Do you know this build heap works in order of n? Why it is working in order of n? Do you remember this build heap works in order of n? And what we do in the build heap? We basically take a heap and we successively do the heapify that we start from here, right? We start the heapify from here, and then we say that, okay, let me just heapify it, heapify it, heapify it, heapify it. Basically, I'm not doing anything for these leaps. In case of build heap, when I write the build heap algorithm, I'm not doing anything for these leaps. So for these n by 2 numbers, I'm not doing any work. That is why n by 2 into 0. I mean, just 0 work I'm doing for these n by 2 numbers. Plus some work I'm doing for this, some work I'm doing for that is okay. So ultimately I just have order of n. Reason being is that theta of n, or order of n. Reason being is that because I do not do any work for the leaf, and these leaves are half of the population, and I'm just getting them free in case of build heap algorithm. That's why it works in just theta of n. And there is another algorithm which successfully build the heap, which takes n log n. And reason being is that does not leverage this particular property that these are the n by 2 numbers at the leaf. Okay. Anyway, let's continue with other questions. Okay. Chiranjeev is asking, what if we have to find the nth smallest? Okay. In the min heap or the max heap. Let's suppose you are taking the max heap. So if you're taking the max heap, then let's suppose this is the maximum that you have, right? And then you know that whatever its height, let's suppose these are the total n numbers. Okay, it might be complicated then. Maybe let me just take uh, any numbers. Okay, let's just take n numbers. Then the height will be log n, right? Okay. So I know that if it's the max heap and you want to find out, let's suppose the smallest number, that I know it must be on the leaf. I mean on the leaf there must be the smallest. If you want to find out the second smallest, then you don't know whether the second smallest, this is the smallest, let's suppose the second smallest maybe adjacent to smallest or maybe in the leaf, or you don't know, maybe it is here also, right? The second smallest could be here also, which means it could be here also. This is the second smallest, this is the smallest, right? So you cannot say anything about the smallest in case of max heap. Actually, this max heap is not even made for the smallest and second smallest. This is made for the maximum numbers. Similarly, smallest can be find here in the max heap. Second smallest can be find here. Okay, you don't know actually. You cannot claim that it must be on the leaf nodes only, or it must not be on the second level, right? It can be here, it can be here, and the smallest can be here. Something like this, right? Definitely, that's a possibility. Similarly, the maximum element can be here. The second maximum can be up to this point. The third maximum can be up to this point. So basically, if I talk about the max heap, then you will say that maximum can be up to this point, second maximum can be up to this point, third maximum can be up to this point, something like this, right? If you talk about the smaller numbers, then you will say the smallest can be like must be here, smallest must be here, second smallest must be below this, right? You don't know, maybe at this level also it could be there, right? Maybe at the leaf only. So second smallest, something like this you can claim. Okay, third smallest must be below this level, third smallest. It cannot be above this level. I mean, it can be if there are repetitive numbers, but it must be one of the repetition must be below this level, which is the third smallest. Why? Because if none of the third smallest is here, right? Let's suppose 1, 2, 3 I am taking. If 3 is not here, then let's suppose 3 is here. Then you have 2 and 1 and 2. Then you will not be able to fill other slots, right? So let's suppose 2 are writing here, 1 you are writing here, what you will fill here, right? So basically, if none of the third smallest is here, then you will not be able to fill other slots. So you can say that the maximum is here, second maximum is up to this level, third maximum is up to this level. If you talk about the smallest must be up to this level, second smallest must be up to this level, I mean below these levels, and similarly, right? Okay. You will be taking n, order of n only. You will be taking order of n. You can't do anything. I mean, obviously it depends on the value of n. If you are saying that nth smallest, anyway, like it will depend on the value of n. If n is too close to this maximum, right? See, if you are saying 1, 2, 3, 4, 5, this is the maximum, and then you say that this is the smallest, and then you say the fifth smallest. Fifth smallest is actually the maximum. Then you will be finding the order of one, order of one, yeah. So it will also depend on the value of n, and this will be just an aptitude question that you need to find out. But I hope you got the idea. Let me move further because there are many problems I want to solve. Okay. If there is any doubt, let me know here, and I can move further. Right? Yes, Satyam, that is correct. We don't heapify n by 2 nodes. Okay. Let's solve this question. This question I have given in the weekly quiz of our data structures. Our weekly quiz data structure quiz that I have given in the Go Classes course. This question is very nice. I have taken this question from some standard university. Let's see this question. This question will be basically helping us to solve one of the PYQ. Okay, so that's why I'm just solving these weekly quizzes question. Otherwise, like I just wanted to solve only PYQ questions in this session. Okay, so let's just continue. What I'm saying, consider the following binary heap. This is the binary heap that we have. Suppose that last operation performed in the binary heap ever was the inserting the key x. Okay, so they are saying this is the binary heap that is given to you, and they have inserted last operation that you have done in this. It was the inserting key x. What are the possible values of x? That's a good question. Do you want to take 1 minute to solve this question? Extremely good question. Just try solving it. Okay, so let me see if you have got any answer. Okay, someone is saying A and D. Let's just check the answer. Okay, I do not have the. Cool. Let's just see what are the answers. So he's saying 19 is the possibility that we have just added. Maybe 10 is the possibility. Okay, 10 cannot be the answer. 10 cannot be the answer. Cool. Do you have any other answer? No. Why people are saying A and D? Okay, strange. Let's just see what is the answer that we are getting here. See, let's just think about it, okay? Let's just think about it. It will help us to solve one of the PYQ. That's why I've just taken this question. So let's just see. See, before inserting any of the node, I mean, just before inserting some node here, it must be empty, right? This hole must be there. This must be an empty hole. And whatever I inserted, could be 19, right? Could be 19. That's not an issue. It could be 19. But whatever it could be, you must have compared, like, let's suppose it is not 19, then you must have compared this. Maybe let's suppose, okay, let's suppose it is not 19. This is something which is greater than 26, okay, which is greater than 26. Let's suppose this is maybe 33, okay. You insert this 33 here. Then what you will do? You will compare, since it is a max heap, right? Okay, it is a max heap. You want to keep the maximum on the top, right? Since it is a max heap, you will compare this 33. If you are inserting 33, you will compare this 33 with this 26, isn't it? So you will be comparing this 36 with 26, and then based on that, you will be swapping these two. You will be writing 33 here, you will be writing 26 here, isn't it? Let me know if that is clear. Tell me if you have to compare. See, suppose you are inserting, maybe I can explain this more clearly. Suppose you are inserting 33, okay, this is 38, this is 35. I'm just making some of the notes. Some of the notes I'm just making. 26, and then this is 25. Cool. Some of the notes I'm making, and let's suppose this is where you are inserting. Okay, I don't know if the very clear. Maybe I can I can do one thing. Okay. Do you want me to draw this diagram? Okay. Actually the diagram is white paper. I mean, it is having the white background, but I wanted to have the black background. So that's why my concern is there. Anyway, maybe what can I do? I can redraw this, right? This is okay. Just give me 1 second. I can just bring the black background also. Let me just change it to the black background because I want to show you some nice illustration. So I think it will be better if I have that black background. Just give me a second. I don't know if it is that much worth, but okay, we are almost done. Cool. So this is the diagram. Then let's suppose this is the heap that I have. May not be that much clear, but I hope you can at least see this, right? Now what I'm saying, let's suppose here you're inserting 33. Okay, suppose you're inserting 33. Then what you will do, you will be comparing this 33, right? You will be comparing this 33 with the 26. You will be comparing this 33 with 26, and then you will say that okay, whichever is greater, since you want to shift the greater on the top, so whichever is greater you will be keeping on the top, right? So you will be swapping this 33 and 26. Now suppose that this is 33, so you will be swapping this 33 and then you will be writing 26 here, isn't it? Let me know if that is clear to everyone. So this is the picture that you have, and then once you swap it, then you will be having 33 here and then 26 here, right? Now tell me, should you be comparing this 33 with 26 only or just with 10 also? With 10 also do you compare when you insert? Do you ever have to compare with the 10? Let me know. No, right? Why you don't have to compare with the 10? Because I already know the 10 is smaller than 26. That's why it is a heap. Otherwise, why will I call this as a heap, right? So I already know that 10 is smaller than 26. I just came to know that 33 is even greater than 26. So why I have to compare between these two, right? So this sibling, with the sibling, I never have to compare. I just have to compare with the parent in case of insertion. Yeah, if you are doing the heapify, do you remember the heapify in the build heap? in that case you have to compare these three, because nothing was a heap, like you have never compared between these two, right? I mean, you have to compare, in case of Heap, you have to compare these three, but in case of insertion you don't have to compare these three, you just have to compare this 33 with 26. So you will be swapping this 33 and 26, something like this, and then you will be getting this, right? So 23 will be 26 will be here and 33 will be on the top. Let's just see that how insertion is working, and then you will get to understand this question. Then 33 and 32, since again this is greater, you will be swapping these two. Do you have to compare this 33 and 22? Never, right? Because you already compare this 32 and 22. You already know that 32 is greater than 22. You just came to know that even 33 is greater than this 32. So you never have to compare between these two, right? Okay. So so you will be basically swapping these two, and then you will be saying that, okay, let's just write 32 here and then 33 here. So finally 32 is basically here. I can say 32 is here, right? And 26 here, 33 is here. Now you will be comparing this 33 and 35. You will say that, okay, see, nothing is, I mean, this is even smaller. So you have to do nothing, right? So basically how you are doing, you are basically first here, you are comparing this whenever you are inserting, then you are comparing this with the parent, then you may swap, right? Then you are comparing again. So now it has become 26. Now you are comparing again that with the parent, then you may swap depending on the value you have swapped it. Now you are comparing again these two, then you may swap or you may not swap, right? Suppose that this is 40, okay, suppose this is 40, then you will be swapping, and then you will be going till the root, right? This is not 40, that's perfectly fine, it will get a stop here. So whatever you are doing, basically in case of insertion, which nodes you are changing, if you are inserting something, then just see here, these are the set of nodes that you are changing. You are inserting something here, and this is the path where you are changing things, right? This is the path where you are changing things. You are changing, you are comparing this as a parent. Maybe you are swapping, maybe you are not swapping. I'm not saying you are swapping. Maybe you will swap, then it will propagate, maybe it will propagate. So maybe something it will be changing. And exactly what it will changing, I will tell you. For now, let me know if this is okay to everyone. That you will be changing somewhere on this path, right? Now let me tell you that what exactly you will be changing. See, let's suppose this is your heap that you have, and suppose you are inserting something which is 33, right? I just inserted 33. So in case of 33, what you will be doing, you will be saying that, okay, ultimately the 33 came here, right? If you remember from that previous example, ultimately 33 came at the place of 32. Actually what happened, that okay, I'm assuming that this is not there, and you are actually inserting the 33, right? Okay, now you're inserting 33. So what you are doing, you are saying that, see, 33 will be coming here, and then as it will be shifting as it is. You're getting my point? As it is. As it is means that there will not no shuffling between these two. Okay. Okay. Which means if this is 32, 32 will be coming here, 26 will be coming here, like that, and 33 will come here. So basically, if 33, if this is the first node, or this is the first node which is greater than 33, then you will be shifting all of them like that directly. Okay. No problem. Directly you shift it. You just insert 33 here. You can do in that way. Suppose, for example, I'm inserting 36. Just try inserting 36 here. I'm sure that what you will be getting is something like this. Just try inserting 36 here, and then you will be getting something like this. I hope that is visible. So you will say that, see, if you insert the 36 here, 36 must be inserted in place of this 35, and then everything actually will go like this. I mean, will shift here. Everything will shift like this. So basically 26 will come here, 32 will come here, 35 will come here, and 36 will come here. Basically you will be just shifting every of the node. I mean, there will be no shuffling between the respective order, which means you will not be shuffling these two just shift down. Okay, this 35 will come here, 32 will come here, 26 will come here, and 36 will come here. Just shifting down. You are just shifting down these three, right? I mean, from this empty location to the first position, which is basically I mean, this is the highest number, which is which is lesser than 36. 36 should be at this position. So from this hole to the root, at max to the root, okay, till this, from this hole to the path, you can just shift down the numbers. If the number is 40, that has to be put here, then finally it will look like this. See, Let's suppose you want to insert 40. Okay, you want to insert 40, then it will look like this. Let me just tell you that 40 will be coming here, 38 will be coming here, 35 will be coming here, 32 will be coming here, 26 will coming here, right? Which means that this 38 will get here, 35 will get here, 32 will get here, 26 will get here, something like this. Let me know if that is fine to everyone. Okay, this is the other way of looking at the insertion, and that will help you for the insertion intuition, that how heap is working, right? So basically nothing gets changed in the heap, only this path from the root to the hole, this path can get changed, and that to just propagate down, right? So all the nodes that may disturb by your insertion is basically along this path. So you might have inserted 38, earlier root might be 35, right? And you might have inserted 38, and then this is the situation that you are getting. See, they are saying that finally it looks like, right? They are saying that finally it looks like this, and you do not know what you have just inserted, right? So that's what they are saying, that it looks like this. This is 19, and you do not know what you have just inserted. So maybe you have just inserted 38. I mean, you inserted 38, and everything was like this, and then earlier this was the 35, this was the 35, this was the 32, and this was the 26, and this was the 19, and this was the empty location. Okay. So suppose that's the case. If this is the case, now if you insert 38, let's suppose this is the case. If you insert 38, then how it will look like? Then you will say that okay, 38 will come here and everything just shift down. So basically, if you insert 38, then it will look like this, right? Basically, whatever you are inserting is actually on this path only. So earlier it might be something like this, and if you insert 38, then 38 will be coming here, everything will just shift out. So whatever you are inserting, that can just change this path, nothing else. That can just change this path, nothing else. Okay. So this is very, very important to understand. And from where, from the same concept, one of the PYQ has been asked. I will tell you how. So what they are saying, what are the possible values of x? What you have just inserted? Maybe you have just inserted 19. Maybe you have just inserted 26. 19 must be there. I mean, if you have inserted 26, then this was the heap. Then this was the heap. If you have just inserted 26 before inserting, 19 might be here. You inserted 26, you swapped them, and then you got it, right? So maybe you have just inserted 19, maybe you have inserted 26, maybe 32, maybe 35, maybe 38. So 19, 26, 32 and 38. But 38 is not an option. So this was the MSQ that I have given in Go Classes weekly quiz. Okay. So those who have attempted weekly quizzes, those who are Go Classes students, they know it already that this was the weekly quiz question. So this ABC is the correct answer here, right? Okay. Now D is not the answer. D is just for the confusion. I have given D. Cool. Now, let's just see the PYQ that they have asked, because I want to focus more on the PYQs. Okay, this is the PYQ for which I just explained all of this story. Now, what they are saying is that consider a process of inserting an element into max heap where the max heap is represented by an array. Suppose we perform a binary search. So, they are representing a max heap by an array. I mean, they are representing by an array. I'm just showing you by the tree for now. And then they are saying that they want to insert something into this max heap. Okay, maybe let's suppose this is the max heap that they have, and then they want to insert something here, right? Now what they are saying, that suppose we perform a binary search. Extremely nice point. Suppose we perform a binary search on the path from new leaf to the root. See, first, this is combining two very, very important things. Whatever we have studied till now in the heap, it is combining both of the things. Tell me, isn't this path is sorted? Isn't this path is sorted in the decreasing order? That's what we know, right? That's why if you want to apply on this path, then you can apply the binary search, because binary search is applied on some function. I mean, okay, let's not worry about the function. Otherwise, the general definition of binary search is that it is applied on a function which is an increasing function. The way we are using the binary search in almost all the cases is basically having the identical function. Okay, otherwise you can apply on any function which is an increasing function. Anyway, okay, my voice is now getting worse and worse. So what I'm saying here, that from here to here, the things are sorted. That's why you can apply the binary search. And then you know that if you are inserting this element, then you only have to deal with the path from here to here, right? So what they're saying is that suppose we perform a binary search on the path from new leaf to the root to find the position for the newly inserted element. See what they are saying that if this is the heap, you want to know that where this newly inserted element will go up, right? It may just be here. Maybe it will go up based on the number. If it is very high number, 100, let's suppose 10,000, it might go till the root, right? If it is very low number, let's suppose it is 1, it might stay here depending on the number, right? So basically they are saying that I want to know the position. Maybe it will go here, maybe it will go here, maybe it will go here. So if we want to know the position, what we are doing, since I know that everything is sorted, I want to know a number which is just, the number which is, you can say, just greater than this, right? Immediate number which is greater than this. So maybe I can apply the binary search here, right? So they are saying if you want to apply the binary search, that you can do for the insertion, the number of the comparisons that are performed. Since this is height is log n, right? And then if you want to apply the binary search, these are the log n numbers. The answer is in general case, for the n numbers, answer is log n. If the numbers are log n, then answer is log of log n. See, doing this question was not a great deal. I mean, you can do this question without all of this information. But when you know that why they are saying that you can do this, then the things are actually making sense. Then you are connecting the dots, and that's where Go classes comes into the picture. I mean, if we are doing this alone, then you might not get that kind of intuition that okay, why they have written this line. See, when I'm doing the hashing question, I'm telling you that why they are saying chaining. When I'm doing any question, like we are doing any question, then we are telling that why they have written this line actually, because these are not just they have written just to make a question. This is actually the procedure which we can actually apply to insert into the heap, right? Okay. So it is actually just to find that where you can insert, but anyway, like I mean, this is just a position, but anyway, you have to shift all the elements in the array. So that's why to shift all the elements, you anyway have to, in the worst case, you anyway have to shift log n numbers or something, right? So that's why this will take anyway, the final time complexity will be the log n if you want to insert, but just to find the position, it is log n, right? If you just want to find the position. Okay, cool. Let me know if you have understood this. The answer is B. And answer also, I'm sure, like these things might not be specified. Like I mean, most of the answers, not most of the answers. Yeah, I can say most of the answers are good on the GATEOverflow, but few of the answers that are missing some information that you can add. Okay. Once you get your gate rank, then I just request all of you to improve the GATEOverflow community, where you just contribute. See, I and Deepak are contributing. Deepak and Arjun sir are contributing. Arjun sir are getting lesser and less time as the day progressing, because he's doing a job. He's having a family and everything he has to manage. So he's a busy person now. And I and Deepak are also getting very busy just because of the classes, just because of the notes and these things we have to prepare, the videos and all. So I want to contribute on the GATEOverflow. I want to improve few of the answers, but I don't find that much enough time. So that's why it is a community. If you all of you do it, then it is a great thing. Okay, let's just continue. So yeah. So this is again a question that I have given in the test, in the mixed subject test, and based on this question, there has been a gate PYQ. So maybe I can just immediately tell you the gate PYQ, and then I will go back to that question. Okay. So let me tell you this PYQ what they have asked. So regarding this PYQ, there are, I mean, I just flipped this PYQ in such a way that you never have to, you will never recognize that this is the PYQ that you have already solved. I just flipped this PYQ in a very beautiful way, and I framed this question. And then what we will do, we will first solve this PYQ, then we will solve this question which has been asked in test. So if you have subscribed to get this Go classes test series, then in one of the test, in mixed subject test, this question that I have asked, the question number is 39. So anyway, let me first solve the PYQ, then I will go to that question. Yeah, thank you. So what they are saying, consider a complete tree where left and right subtree of the root are max heaps. See what they are saying, complete binary tree. This is very important. Okay. extremely important thing. They are saying complete binary tree. So which means that you are having complete means that this thing, right? I mean, all labels are full except the last. I mean, last can be full, last may not be full. This is the complete binary tree that you are having. Now, what they're saying that left and right subtrees of the max heap are already heap. So they are saying that this is a heap, this is a heap, this is also a heap. Okay, these two are actually heap. And what you need to do, you need to convert the everything to heap. The lower bound for number of operations to convert a tree to a heap. See what they're saying it is a complete binary tree. That's very important. That's very important point to understand here. If it is not a complete binary tree, then you cannot do this question in the required time complexity that they are asking. Okay, so complete binary tree means, I mean, last level maybe not filled. Okay, something like this. They are saying that this is a heap. Okay, they are saying this is a heap. They are saying this is also a heap. It is given to us that these two are heap. Heap means that heap means what? That the numbers are in the decreasing, increasing order. I mean, it follow the order property, whatever the order or heap property that we have. It also follow the structure property. Structure property means that every level is full except the last level. So anyway, it is a complete binary tree. So they are saying that it is a heap. It is a heap. If these two are heap, then you want to make all this whole thing as a heap. You want to make this whole thing as a heap. How much time complexity you can do it? In how much time complexity you need to do it? You can do it. You can just heapify, right? You can just heapify on the root, and then you can say that this will just take log n, right? This will just take log n. You just heapify here. So basically, in other words, I can say if there are two heaps, okay, let me go to that question which I have asked. So before that, I can say that the lower bound, the minimum time that you will be taking is basically you have to take. Okay, do you really have to take log n? Let me know. The lower bound on number of operations to convert the tree to heap. Consider complete binary tree where left and right are heaps. So they are saying that at least log n you will require. But what if it is already heap? What if heapify just say, okay, yeah, it is interesting. It is quite an interesting question. So let me know if you have understood this. See what they are saying. Okay, so let me just take a complete binary tree. Let's not worry about these numbers. So suppose that this is the complete binary tree I have, and let's suppose some of the nodes are not here because this is the complete binary tree. Now this question is quite interesting. I did not know that this question is that much interesting. So now this is a heap. This is given to us. This is also a heap which is also given to us. Now they are saying that you have to perform heapify here. Let me know that what is the lower bound. Lower bound means that in even the best case you have to do it basically, right? Even in the best case you have to do it. What do you think? See what's going to happen here, that you will check. Let's suppose that whatever min heap or max heap, let's suppose that you want to convert this to a min heap. These two are min heap. Okay, this is min heap, this is min heap. Let's suppose this is already this is some number which is, let's suppose 5, which means it is a minimum number here. This is some number, a minimum number here, right? This is some number which is, let's suppose maybe anything, right? Maybe 11, which is a minimum number in this heap. This is 5, this is 11. Suppose this is 1. this number is 1. Okay, if this number is 1, then I think you're done, right? I mean, you have just compared with the minimum, and you can just stop it here, right? I mean, why? Okay, let me just check it. Lower bound for the number of operations to convert the tree to a heap. Left and right subtree, okay, a root of the root or max heap or mini heap, whatever, right? So let's just take it max heap, doesn't matter. So if these two are max heap, you want to convert that to a max heap. Let's just check if max heap is having some difference. So let's suppose it is a max heap. Let's suppose it's some number 100, which is the maximum number in this heap. This is, let's suppose, 50, which is maximum number here. Let's suppose this is 150 or maybe 200, which is actually greater than all of this. If this is greater than 100, then I'm done, right? This is greater than 50, I'm done. Why I need at least log n? This is my confusion. Here the lower one implies the best algorithm, which works for all the cases. Consider a complete binary tree where the left and right subtrees of root are max heaps. The lower bound for the log n is the upper bound. I mean, this log n is the upper bound. They are saying lower bound. So if I'm saying lower bound is omega of log n, let's suppose if I'm saying this, then what does this mean of saying? It means I'm saying that lower bound is greater than or equal to log n. I don't think this is correct. Yeah, I don't think it is correct, to be honest. Should be upper bound. Okay. Anyway, let's just skip this. I like personally, I don't think there might be something that I might be missing. Not sure. I also might be missing something, but I think if lower bound, let me just give me a second. Lower bound is greater than or equal to. I mean, if lower bound is equal to this, lower bound means, I mean, this is definitely log n is upper bound. You cannot, I mean, you do not need to greater than log n. That's for sure. But do you need at least log n? So, what do you think? Like, I mean, what should be the answer? Is this a lower bound or the upper bound? Maybe they mean this is the lower bound. Okay. Let me just check if there is some comment on GATEOverflow. Okay. So Arjun sir is having some comment on the GATEOverflow. Just write that comment here. So he's saying that need to get a good reference. I mean, there. Okay, he is also looking for a good reference. But for what I have seen, the lower bound is for the best case input, right? If an algorithm is given, otherwise it assumes the best algorithm and the worst case input. Okay, maybe. They are talking about the worst case. In the worst case, what would be the lower bound? Okay, if the case is not given, then by default, Arjun sir is saying that we need to take the worst case. So let's see one of the comment. Yes, sir, you are correct about the lower bound of a problem. Okay, so there is some reference. Basically, you know what is the problem and what is the algorithm. So the problem is, let's suppose if I talk about the problem, then the problem is sorting. Sorting is a problem, right? It is a general problem. It can be solved using some algorithm, maybe merge sort, quick sort, like that, right? Quick sort. So basically, these are the algorithms. The problem is general, right? Now, making it heapify is a general problem. Now you can do it using any of the algorithm. Obviously, the best algorithm is heapifying it, right? Heapify is best algorithm, best thing to do it. Thing here. Anyway, let me just continue. So here the lower bound means that you are talking about the worst case. Anyway, from the options it is clear, right? Okay. So we have to choose the best option, and the best option is omega of log n. Cool. Let's just see that what I have asked here in the subject test, in the mixed subject test. So I have said the same thing. What I have just tricked out one thing. So let me just tell you what I have done. Okay, this is very nice question that I have formed using this PYQ. Let me tell you what this question is saying. Consider two binary min heaps which are basically containing 2 power L minus 1 and 2 power R minus 1 nodes. So what I'm saying, there are two binary min heaps which are complete, which are perfect actually, right? Which are perfect. One binary min heap is this. Another binary min heap is also perfect, but it could be very large. I mean, this is something like this. Now suppose if I just ask you that can you just combine these two binary min heaps to get a min heap, then you will say it's not that much trivial. Why? Because if you want to actually do it, then in the heap all the labels are full, but here if you put it here, then see these labels are not full, right? So it's not trivial if you take two binary min heaps to make a binary min heap finally, right? It's not very trivial. You have to use a build heap algorithm that will take order of n. There is no shortcut also. Okay, cool. So if you have two min heap, this is also min heap, then you cannot directly combine something like this. But if I just say that you have two min heap of same size, which means I say you have one min heap this, another min heap you are having this, these two sizes are same, which means that, and if I want a complete heap out of it, which means what you can do, all the labels are full here, you can just plug in, you can just remove one of the element from here, make it a root. Okay, make this a root, whatever is this element, let's suppose it is a, make this a root, and then heapify here, right? Heapify here, isn't it? Can you not do this in log n? Do you need order of n? Do you need to build, do you need to put this heap in an array, this heap in an array, and then do you need to put both of the heaps in one array, and do you need to just build heap? No, right? What you can do, you can just plug in, you can just plug this out, sorry, not plug in, you can just plug out this particular element, whatever it is, on the rightmost side. Okay, because both are having the same height, so it will not be a problem to violate any of the structure property of the heap, because all of the levels will be full. So you can just plug this out, you can put it here, and then you can say, then you can apply the heapify, isn't it? Okay, so this is one thing that you can definitely do. Now what I'm saying here is that, suppose that if two heaps are of different size, let's suppose this is very small, this is very big, then it is not possible to just plug out this and you pick it here, then you cannot heapify it here, because this is not, these labels are not full, right? So if there's a problem, I mean, if sizes are different, you cannot do it. If sizes are same, you can do it, right? Okay, this problem is saying the same thing. They are saying that you have two min heaps of this size and this size. We want to build a new min heap containing all the elements of both heap. It is known that either L equal to R, which means both are of the same size, or L minus R. The difference between L minus R, L is basically you can say the height here, okay, a height, or height plus 1 or height minus 1, whatever. So basically they are saying either both are equal, or maybe either both are exactly equal in terms of nodes, or maybe one of them is this, another one is just one lesser than height, okay, one lesser height. If see if you have two heaps, if both are equal, then I just told you what to do, right? You just plug this out, put it here. If both are not equal, if one is let's suppose this one is or maybe this one is some lesser height, one lesser height only, okay, not much, just one lesser height. If this is just having one lesser height, in that case what you can do, then also it is fine. Why? You can just plug in, plug out whatever is having the maximum height. It is having more height, you can plug this out and then put it here, right? See, if both are having equal height, you just plug it the rightmost side. If both are having not equal height but just one lesser than this, then also you can do it. You can just plug this out, because ultimately it can go to the root, and then whatever will come here will anyway come here, right? So that's what this question is asking. If either they are having the same height or they are having the difference of height of 1, then what is the best algorithm that can make it as a heap? Then in the best case, in the as a best algorithm, you don't have to use the build heap. You can do it. The most efficient algorithm will take order of log n only, right? Order of log n, where n is the size of new heap. You don't have to do it in order of n. You don't have to use the build heap. So that's what this question is asking. Let me know if that is clear to everyone. Okay, cool. Okay, let's just move further since we need to do many of the questions. See, this the answer is A. We can merge two heaps by just making one of the rightmost side of the right heap as the root, or whatever I have just explained. It is written here. So anyway, you got the idea, right? So if both are having equal height, which means if L equal to R, then you can plug this out. If L is not equal to R, let's suppose if both are having, this is having just one lesser height, then you can plug whatever is having a higher height, right? You can plug this out, put it here. Okay, let's solve this question. This question has been asked in GATE 2016. This is also very good question. Let's try solving it. A complete binary tree, binary min heap is made by including each integer 1 to 1023 exactly once. Okay. The depth of a node in a heap is the length of the path from the root to the heap node. Thus the root is having the depth 0. They are saying it is having depth 0, and the maximum depth, which then they're asking that if you are having 1 to 1023, all numbers are distinct, then 9 can be present at which depth. Okay, see, in this heap how many, like what will the maximum depth, basically what is the height or the depth of this heap? You can say that this 1023 is 2 power 10 minus 1, which means you can say that there should be this is 2 power 0 plus 2 power 1 till 2 power 9, right? So this is 2 power 0, which means you can say then 0 1 2, this is 1 height, 2 height. Okay, you can say that at max 9 depth could be there. 9 depth, I mean this particular heap will be the complete binary tree, which will look like this, right, with the 9 depth, isn't it? Why it is 9 depth? Because at depth 0 I have one element, 2 power 0. This is one element. Here I have two elements, right? So 2 power 1. So at depth 1 I have two elements. At depth 2, 2 power 2. At depth 3, 2 power 3. At depth 9, 2 power 9 elements. And finally I will be having these many elements, which is basically 1023. I have 1023 elements. So which means I have depth 9. So this is depth 1. Okay, this is depth 1. Similarly, I can say that I have till depth 9. This is depth 2. This is depth 3. Let's suppose this is depth 9. Then where can 9 be present? That's what they're asking. Okay. If 1 is present here, at max, where can it present? Then 2, 3, 4, right? Okay, 4 can be present at depth 3. Similarly, 9 can be present at max, it can be present here. It can be present at depth 9. 9 can be present at here. Why? Because I have to have everything in the increasing order. At max, at minimum, it can be presented just after this. At minimum, it can be present at this level, not an issue. But at max, it can be present at depth 8 only. Okay, till depth 8 only. Because 2 can be present till depth 1, 3 can be present at max, I'm saying. It can be present at depth 2, something like this. Twinkle is asking number of possible mini heaps. These kind of questions I might be solving. I don't know if I have that in slide. I know a PYQ I didn't understand, hence I'm asking. Okay, currently I do not have that number of many heaps because once or twice they have asked. If you are a Go classes student, then you can watch our video. So there I have explained this in a great detail, that how to find out the number of many heaps. Okay, if there is anyone, then you can definitely vouch for it. Let me know if things are clear or there is some problem with my internet. Okay, cool. So let's just continue. So I think the answer should be 8, right? That was an easy question. 8 is the answer. This is the maximum. Minimum, if they ask, then minimum is 1. Okay. I think this is an interesting question. Let's just see the further possibilities here. This is depth 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. I hope you can see the whole tree. Cool. This is I mean depth 9. Now let's just see something here. So where can 103 be present? 1023 be present? I think at the last, right? At the last only it can be present. Can it present in the middle? No, 1023 cannot be present here, because then what you will be writing here? Because everything is in the increasing order, strictly increasing order, because numbers are distinct. Okay. So 1023 have to be here. Now, similarly, if I ask you that what is the at minimum, see 1023 has to be here, 1022, 1021, 20, 19, 18, 17, 16, 15. Okay, if I ask you minimum, where can 1015 can be? Let me know. See, can it be here? If you are writing 1015 here, then 1016 can come here, 1017 can come here, 1819, 20, 21, 22, 23. Can you write 1015 here? That's my question. No, right? You cannot write it here. Reason being is that whatever you are writing here, okay, there must be, you can, since it is complete binary, there must be many numbers which are greater than this number, right? Not just one path, every path, right? Not just one path, every path should be greater than 1015. So basically the total numbers are here 1013, right? So basically the total numbers are 1023. One is root. Then on the left side of root you have 1022 by 2 numbers, which is 511. Okay, you have on the left side of root you have 511 numbers. On the right side of root you have 511 numbers, right? Here you have 511 numbers, here you have 511 numbers. So this is your heap. That's how it looks like. Now whatever you are writing here, there must be, since everything is in the increasing order, there must be, whatever you are writing here, there must be, since you have to fill this, right? There are 510 numbers here, right? So 510. So there must be 510 numbers which are greater than this, right? So you can write, I mean, you can just calculate it. Maybe you can write 510 or something. You may not be able to write lesser than 510. Okay. So basically, whatever you are writing here, you must make sure that all of this, since it is a greater than, it is lesser than all of this. So because all of this are strictly greater than this number, and total here, since it is a root, okay, this was the root. That's why since it is perfect, that's why I'm dividing into two parts, which is basically 511, 511. And then what I'm saying, that whatever your like these are the 511 nodes, these are the 511 nodes, and then excluding this, this will be 510 numbers, right? The total will be 510 numbers. So whatever you are writing here, there must be 510 numbers which are greater than this, right? So which means if 1023 is there, then this is one number, two number, which means I think 510. Can you write 510 number here? 510 here. Then you need to think about it. Then you will say that okay, if you write 510 here, then 510. Yeah, I think most probably you can write, right? You can definitely write 510 here because you have 510 which are greater than this. You need to have 510 which are greater than this. Okay, let me know if you have understood this. So basically, they can also ask you these kind of questions, right? Cool. So you cannot write 1015. That's my point. Okay, just don't look at just one path. You have to look at all the numbers. Okay. Now let's do this question. This question is an interesting question. Reason being is that I mean this was the AIMT1 question, and this is not the reason obviously. But the reason is that there has been a PYQ just based on this question, or maybe vice versa. Like I have taken this question from my standard university and using the PYQ, I just mixed that question for the AIMT1. So let's just solve this question, see what it is doing, and then we will be solving one question that has been asked in GATE 2019. And this question and that AIMT1 question that I have just talked about, these both the questions are very similar. Okay, once you solve one of them, then you will be able to solve this question. Maybe let's just do this. How many of you have done this correctly? Let me know. How many of you have done this correctly? Okay, okay. So let's just do this. What they're saying, as one is one statement, there exists an algorithm to build the binary heap from an unsorted list in order of n time. So they're saying that you can build a binary heap. Yeah, definitely, right? That was an easy question. So you can do it on order of n, which means you can do it in theta of n, which means order of n. So that's the S1 is good. S1 is true. S2 is interesting. There exists an algorithm to build a binary search tree. Okay, you want to build a BST, binary search tree, using unsorted list in order of n time. That is false. Why? Let me tell you. Okay, so they are saying that you can build BST in order of n time. This is what they are saying. Can you? I mean, this is what question is. Okay, okay. So why this is false is because let's just prove this using a very nice, nice counter example or very nice claim. Suppose that is true. Okay, suppose there is an algorithm A that can do it, which means you give any unsorted list here. That algorithm A can give you BST and it is just taking order of n time. Suppose there is an algorithm. Suppose there exists an algorithm that can actually do this task, which can you just give them you just give the unsorted list to that algorithm and that will give you the BST. Suppose there is one. My claim is that there cannot exist such algorithm. Reason being is that you have any unsorted array. Suppose you want to sort it. What you will do? You will give it to A, which will anyway take order of n, right? I mean, that's our claim that this exists. It will give BST to you. You will just take the in order of this, which you can anyway do in order of n, and then in order that is sorted for the BST. So what you can do, you can convert that unsorted array to a sorted array using the help of this algorithm in order of n. Why? Because here you are taking order of n, here you are taking order of n, and then finally ultimately you will be taking order of n, and then you can actually sort it in order of n, which is not possible for the random list, right? Yes, yes. So yeah, everyone is getting now. So we cannot sort it. So from unsorted to sorted, you cannot go in order of n. So that's why there is something wrong we are doing. Obviously, we can definitely do the in order, but maybe this does not exist then, right? So that's why I will say there cannot exist any algorithm such that it is doing the same task. That's why S2 is false. Okay. So S1 is true and S2 is false. So A is the correct answer. How many of you did it correctly in AIMT1? That's the question number 32 that we have asked in Go classes AIMT1. How many of you did it correctly? Now, let's just see what this question is asking. They are saying the second element, second smallest in max heap is always at the leaf. No, I don't think, right? Always at the leaf. Second smallest is always at the leaf, right? Even if it is repeating or whatever, smallest is always here. I'm 100% sure. Second smallest can be here also, right? Can be here. So second smallest is below this. So if you remember that particular uh, diagram that I made, I think uh, I think that one. The second smallest will be below this, right? This is the diagram that where we have talked about that what are the possibilities for first smallest, second smallest. Okay, so maybe you understood this. Then let me go to the same page. Okay. So here I am saying the second smallest need not to be on the leaf. It can be in the between also, right? It can be it can be here also. It can be in the second last level also, second smallest. Cool. So I think it is not true. The second largest element in the max heap is always the child. Second largest is always the child of the root node. Ah, yeah, this is interesting. Let me know if that is correct. What do you think? Child of the root node, second largest. It is on n log n. You cannot do it in n. We will be doing it, okay? We will be doing one question regarding that. So someone is asking what is the time complexity to build a binary search tree. We will be doing one question and that will take n log n. There is one PYQ, don't worry. So see the second in the max if they are talking about they are saying the second largest. So the second largest must be at this level, which means it could be either this, could be other. So that's why it is true. Nice one. This was false. Okay. Yeah, these two are also nice. A max heap can be constructed from binary search tree in theta of n. See, you can construct from even the unsorted array, right? So yeah, theta of n you can definitely do it. I mean, you do not need to take the property of binary search tree. You put that binary search tree in the array. You just apply the build heap, right? You can definitely do it. You do not need a binary search tree. If they are giving the binary search tree, maybe it is not useful for you because there is no relationship between binary search tree and the max heap. Okay. So the binary search tree information is not useful for you here. Yeah, this fourth option is extremely interesting, by which I made one of the AIMT question. What they are saying, a binary search tree can be constructed from max heap. Can you construct a binary search tree from a max heap in theta of n? So let's just see if that is true. Okay, can you construct a binary search tree? Suppose that is possible. Suppose you can construct a binary search tree from a max heap in theta of n, which means you give a max heap to this and this will give you binary search tree. Suppose there is some algorithm A in theta of n, you can do it. What will I do? I will take an unsorted array. Okay, I will give to build heap algorithm. I will get a heap. I will get a max heap in order of n. Right? Suppose there is some algorithm something like this. Then this algorithm A, can give me BST in theta of n, right? Then I will use the in order and I will be getting the sorted array in theta of n. So everywhere I am using theta of n, theta of n, theta of n. So I can convert the unsorted to sorted in just 3 into n, right? I mean theta of n, isn't it? If there is some algorithm. So obviously this algorithm cannot exist. Isn't it a very nice question? Yes, Aru, that is correct. So Aru Supacat, there is some user. So who is saying that unsorted to heap and then to BST, then to in order, and that's how you can sort it. Yes, and that you can do it theta of n, and that's why obviously this kind of algorithm cannot exist, right? So that's why it is false. So the similar question I have asked in AIMT, right? This is the similar question. I do not remember the marks. I think I kept it for 1 mark only, because I have not made much of the confusion here. I just S1 was very straightforward. S2 was little tricky, so that's why I just kept it for 1 mark. Okay, because only one of the option I was asking if you can solve it. Cool. By the way, how's your preparation going on? Are you guys ready for AIMT 3? So AIMT 3 is going to be I can say it is going to be short, crisp, and conceptual, but not lengthy, which means that we will make sure that on average, you should be completing your paper. Okay, paper should be completed in 2 hours, or at most 2 hours 10 minutes. 10 minutes, and then you can do some of the questions which you have not finished, right? So if you have done good preparation, then we will make sure this AMT3 is just like gate, where if we have done good preparation, then in gate also generally you can do your paper in 2.5 hours mostly, right? I mean 2 hours 30 minutes at most, and then you can do some of the remaining question. So we will just make sure it is just like gate 2020. Let me know if you guys are excited. Okay, so let's just continue. Let's just continue with this question, right? Okay, so this is linked list question. Let me see what else I have here. ABL trees linked list. Some of the good question that I want to solve. Do you want me to solve it in the morning? I mean, we have already taken, I think, sufficient time. Let's solve the remaining questions in the morning. I will make sure that I'm solving all of the questions which are tricky. Just attend this class in the morning at 10 a.m. Okay, and we will make sure that we are finishing all of the good questions. So I'm just taking the good questions, sorry about it if you feel that I'm not taking the trivial questions. Like, you can just put the comment here if you have understood things, if you what you want me to bring in the morning 10 a.m. Class. Okay, there will be just one last data structures marathon. For algorithm, I might conduct, don't worry, for algorithm, I might conduct on the same day or the later day. But for the data structure, this is the last class. And for algorithm, I will just suggest you to watch this playlist. This is my request. Like, this is very good playlist for DFS and BFS. Just watch this 1, 2, 3. Okay, this is 3 is 2 times. It is actually just one lecture. So just watch this 1, 2, 3, 4, 5, 6, 4, 5, and why it is 5 also 2 times. Okay, sorry, it is a screenshot that I've taken. So okay, so this is 4 is this 5 is also once. So just watch this 1, 2, 3, 4, 5 lectures which are DFS, BFS lectures. Okay, watch them once. Okay, see, eigenvalue session. Let me just tell you that eigenvalue session is already uploaded. You can just watch it. There is no point in repeating. That's why I'm not telling. Okay, so eigenvalue session, don't worry about it. I have uploaded it. You can watch it. And let me just announce you a few things that what we are going to do. That's my promise. Whatever, okay, whatever happens, I will just make sure that my throat is okay, like I'm able to speak. That's the only requirement that I know, that I want to have. Whatever happens, I want to cover few things which are cache me. Okay, there are 65 cache questions in the gate PYQs which are dealing with arrays, loops, cache latency, right? Write back cache, write back cache. Some questions are related to set bit, index bit, something like this, right? Index bits. So there are 5 6 different types of questions we will be solving in one marathon, these 65 questions. This is my promise. And for the pipeline, Deepak will be taking one session. For the pipeline, Deepak will be taking one session. So for the cache and pipeline, we will make sure that you do it very correctly. Another thing that we will be doing, basically from my side, I generally take the subjects which, let me just tell you the subjects which I take, C, DS. So I will tell you my schedule, that what I'm planning: linear algebra, probability, operating system, CN, and yeah, compiler. And in the COA, I just taken this time I've just taken cache. Okay, and yeah, I think that is in the compiler I have taken the front end. So these are the subjects that I take. Okay, so this LA is done. OS already available, a very nice, very nice, okay, already available, a PYQ series. I have solved all PYQs there. If you do not have time, this is my personal recommendation: must watch 2 hours of multi-level paging, and let me know how you felt it. Okay, multi-level paging. If you have time, then you can watch fully. Then this is must watch. On the second priority, if you have time, then you can definitely watch the thread and system call lecture, PYQ lecture. So here I have already solved the PYQ. So I will just keep it as a last priority because that is already available on the YouTube. Okay, so that's why I will keep it as a last priority. I will say that it is also done. CN is anyway done. Okay, from here DS I will be doing tomorrow. I will make sure the DS is done tomorrow. Then from my part, my priority is that, okay, these are done. Remaining is C, algo, probe, and computer organization, and maybe compiler. Maybe compiler you don't need, right? Compiler, I want to bring some nice concepts to you, but I don't think you need it at this point in time. So let's not worry about the compiler. So from my side, I can say, I mean, Deepak has his own plan, but I'm just telling you my plan, that my priority is that the remaining, let me just write the remaining ones: algo and C, COA, right, and the probe. So DS, I will make sure that we finish tomorrow. Now in algo, already DFS BFS available. Extremely nice playlist. Just watch it. Okay. See, this playlist is very nice. Just watch 4-5 lectures. DFS BFS, you will never ever have to remember any theorem. And I actually, like, just postmortem. I just did a postmortem of DFS BFS. So watch it. Okay. So here DFS BFS finished. And also the digestion algorithm here. Digestion algorithm, this particular video, extremely nice video, let me tell you. Extremely nice video. Similarly for MST, extremely nice video. Similarly for Mersot, if you have time, just watch it. I have just solved the PYQ. Okay. Anyway, you are solving the PYQs. So just watch it. Definitely worth it. So the remaining thing in the algo, I will be doing, but I will not be doing whatever I have covered, because that will just take a little bit time. So my priority, this is remaining. Out of this, my priority is COA. Okay, COA cache. My priority is this, and then once this is finished, okay, so let me write in increasing order. First DS tomorrow definitely, then COA cache day after tomorrow, and then probability random variable. I'm getting many requests. Let me tell you that probability linear algebra, these are the two subjects, probability linear algebra, calculus. These are the 2-3 subjects which are my area of expertise, in the sense that I have done that courses in ISC. I have lived that life, you can say. Okay, I have worked at Amazon as an applied scientist, so you can say that's in my blood. I mean, probability, whenever I see probability, I just feel so comfortable. Similarly for the linear algebra, so these things are, I mean, I like it very much. So that's why, like, I like to teach it also. I mean, I will like to teach it. So, and I'm also getting a request for the random variable. I will make sure that you will first time you will understand that what is a random variable. I mean, see, the name itself is saying random and variable. So you will get to understand that why we say it random and what is variable here, right? I mean, it seems like it is a function. I will tell you why it is a function and why it is called random variable. I will make sure that I do it. So this is tomorrow, this is day after tomorrow, and then this is on 27th. This is my plan. That's all, right? I mean, this I will be, okay, sorry, this I will be finishing, for algo and C. I will keep it at last priority. Let me know if that is okay. I mean, till 27 I want to finish it, and then I need some time, maybe 28 I need to fix that AIMT. I cannot do much here. I need to make AIMT, so I might need to take a gap here. And then after AIMT, maybe I can take one or two more class if you want for Algo and C, right? Let me know if that suits you. Okay. So I hope you understand. So Mr. Singh is saying that multi-level paging was awesome. So okay. So thank you everyone. Just take care. Let me know if you have understood everything. If there is any doubt, you can just comment it out. Just let me know that things are fine. Just do one thing. Below this video, just comment it out that what you want me to bring in the morning DS session, and just let me know if you have understood whatever I talked about. I talked about, I think, heap and hashing, right? Hashing. Tomorrow I'm going to talk about other data structures. Just please comment it out. It will just help me to get more motivated to just do more. Just do a little bit of more efforts. Anyway, we will be doing the efforts, but if you just comment it out, it will be very nice.